So now we are going to learn about the two-port networks. See, in the two-port networks, the first thing we are going to learn about the Z parameters. Z parameters is also called as the open circuit impedance parameters. So Z parameters is also called as the open circuit impedance parameters. Suppose this is a two-port network. So here this is the port 1 and this is the port 2. The voltage polarity is V1 plus minus V1 plus minus V2, I1 and I1. This is I2 ingoing and this is I2 outgoing. So this is the basic circuit for everything. We are going to follow this same network. So now here for Z parameters we are going to take here V1, V2, I1, I2. So this is Z11, Z12, Z21 and Z22. So therefore if you write in terms of these equations, we are going to get V1 is equal to Z11 into I1 plus Z12 into I2 and V2 is equal to Z21 into I1 plus Z22 into I2. We are going to get this equation. So therefore here V1, V2, I1, I2. So Z11, Z12, Z21 and Z22. See, and when network is symmetrical, see, a network is said to be symmetrical only when Z11 is equal to Z22. See, whenever these two parameters are equal, then we say that the network is said to be symmetrical. But if the network is reciprocal, then definitely Z12 is equal to Z21. So therefore these components are equal means it is a symmetrical, and when these two components are equal means it is a reciprocal. So therefore we can say this is symmetrical and this is reciprocal. And here you can see clearly here V1, V2 are dependent variables, whereas I1, I2 are the independent variables. So therefore V1, V2 are going to depend upon the I1 and I2. So therefore we say V1, V2 are dependent variables, whereas I1, I2 are the independent variables. So simply we can say V1, V2, I1, I2, this is Z11, Z12, Z21 and Z22. So this is called as the Z parameters for this two-port network. So Z parameters is also called as the open circuit parameters. A network is said to be symmetrical only when these components are equal, which are the Z1 is equal to Z22. A network is said to be reciprocal only when these two components are equal, which is Z12 is equal to Z21. And these two I1, I2 are the independent variables, whereas V1, V2 are dependent variables. So now we are going to learn about the another parameter, which is the Y parameters. It is also called as the short circuit parameters. Suppose there is a two-port network with the same convention, which is plus or minus V1, plus or minus V2. This incoming current is I1 and the outgoing current is I1, and here incoming current is I2 and the outgoing current is I2, same as the previous one. But here just we are going to interchange V1, V2 and I1, I2. So we are interchanging that this is from V1, V2 to I1, I2. So if we interchange these two columns, then we are going to get the Y parameters or the short circuit parameters. So just we have interchanged the V1, V2 and I1, I2. We got I1, I2, V1, V2, Y11, Y12, Y21 and Y22. So if we expand into equations, we are going to get I1 is equal to Y11 into V1 plus Y12 into V2, and I2 is equal to Y21 into V1 plus Y22 into V2. Same property whereas the Z matrices. It is following the same properties like the Z parameters, which is when network is said to be symmetrical only when Y11 is equal to Y22, and network is said to be reciprocal only when Y12 is equal to Y21. Whereas V1, V2 are now independent variables, whereas I1, I2 are the dependent variables. So therefore we can say, see, if you know Z, you can easily figure the value of the Y, because Y is equal to always Z inverse or Z is equal to Y inverse, because both are inverse matrices. So therefore V1, V2 are the independent variables, whereas I1, I2 are the dependent variables. So now we are going to learn about the T parameters or ABCD parameters. T parameters is also called as the transmission parameters. Suppose there is a network, and yes, this is same as the previous network, which is there plus or minus V1 plus or minus V2, incoming current is I1 and outgoing current is I1, the incoming current is I2 and outgoing current is I2. So now the equations for this T parameters is here V1 I1, V2 I2, V1 I1, V2 minus I2, A, B, C, D. So we are going to get like this V1 I1, V2 minus I2, A, B, C, D. This we are going to call it as the matrices, or we can say ABCD matrix is going to represent in this way. So if you do the expansion of this into equations, we are going to get V1 is equal to A V2 minus B I2, whereas I1 is equal to C V2 minus D I2. So this is V1 I1, V2 minus I2, A B C D. A network is said to be symmetrical only when A is equal to D. So whenever A is equal to D, we say that the network is said to be symmetrical. whereas a network is said to be reciprocal only when then determinant of this matrix is equal to 1, which is AD minus BC is equal to 1. So therefore, a network is said to be symmetrical only when A is equal to D, and a network is said to be symmetrical only when the determinant of this matrix is equal to 1, which is AD minus BC is equal to 1. So you can see clearly here V2, I2 are the independent variables, whereas V1, I1 are the dependent variables. Now we are going to learn about the T dash parameters. It is the reverse of the T parameters, which is here same network plus or minus V1 plus or minus V2, incoming current is I1, outgoing current is I1, incoming current is I2, and outgoing current is I2. So now what we are going to do is here, just we are going to interchange the two columns. So therefore here we are going to get V2, I2, here V1 minus I1. So these matrices are going to become A dash, B dash, C dash and D dash. So if we expand these equations, if we expand into equations, we are going to get V2 is equal to A dash V1 minus B dash I1, whereas I2 is equal to C dash V1 minus D dash I1. So a network is said to be symmetrical only when A dash is equal to D dash, and the network is said to be reciprocal when A dash D dash minus B dash C dash is equal to 1. So therefore, we can say if this matrix is determinant is equal to 1, we say that matrix is said to be reciprocal, same as the ABCD parameters. So if you know Z, you can easily find value of Z. If you know T, you can easily find the value of T dash. Whereas because these T and T dash are inverse of each other, so therefore T is equal to T dash whole inverse, or T dash is equal to T inverse. So you can see clearly now V1, I1 are the independent variables, whereas V2, I2 are the dependent variables. So same thing I have written, which is V2, I2 are the dependent variables, whereas V1, I1 are the independent variables. So now we are going to learn about the H parameter. So for the same network, plus or minus V1 plus or minus V2, incoming current is I1, outgoing current is I1, incoming current is I2, and outgoing current is I2. Suppose I have already told you this one is V1, V2, I1, I2 for the Z parameters. So now for this, we have to just interchange V2 to I2 and I2 to V2. So therefore, you have to interchange these two components. If you are going to interchange these two components, then we are going to get that is called as the H parameters, which is V1, I2, I1, V2. Then we are going to get here H parameter, which is H11, H12, H21 and H22. This is the only thing that you need to interchange from the Z parameters. Then we are going to get the H parameters. So if we expand into equations, we are going to get V1 is equal to H11 into I1 plus H12 into V2, and I2 is equal to H21 into I1 plus H22 into V2. So a network is said to be symmetrical only when the determinant of this matrix is equal to 1, which is H11 into H22 minus H12 into H21 is equal to 1. And the network is said to be reciprocal when here H12 is equal to minus of the H21. So a network is said to be symmetrical only when the determinant of this matrix is equal to 1, and it is reciprocal when H12 is equal to minus H21. And you can see clearly here I1, V2 are the independent variables, whereas V1, I2 are the dependent variables. So this is the last parameter of the two-port networks, which is G parameter. So for the same network, this is plus or minus V1 plus or minus V2, incoming current is I1 and outgoing current is I1, incoming current is I2 and the outgoing current is I2. So therefore you can see clearly now just you have to interchange the two columns from the H parameter, we are going to get this matrix. So just we have interchanged these two columns, we are going to get I1, V2, V1, I2. This now we are going to get the matrix of G11, G12, G2 and G22. So if we expand the equations, we are going to get I1 is equal to G11 into V1 plus G12 into I2, V2 is equal to G21 V1 plus G22 into I2. So it is same like the H parameters, which is a network is symmetrical only when the determinant of this matrix is equal to 1, which is G11 into G22 minus G12 into G21 is equal to 1. And the network is said to be reciprocal when G12 is equal to minus G21. And you can see clearly this is V1, I2 are the independent variables, whereas I1, V2 are the dependent variables. So now if you know H parameter, you can get the G, which is G is equal to H inverse or H is equal to G inverse. So simply if you know Z, you can easily find Y. If you know Y, you can easily find Z. Similarly, if you know T, you can find T dash. If you know T dash, you can easily find T. Similarly, if you know H, you can find G. If you know G, you can easily find H, because they are same manner, means they are inversely related to each other. So now here I have already written, which is Y matrix is equal to inverse of Z matrix, or Z matrix is equal to inverse of the Y matrix. And similarly, T dash is equal to inverse of T matrix, whereas T is equal to inverse of the T dash matrix. G is equal to H inverse, and similarly H matrix is equal to G matrix inverse, because they are inversely related. So therefore Zy, T dash and Hg. This is the way that you need to remember. So now we are going to find the what is the Z parameter of the T network. So we are going to get the expression of the Z parameter of this T network. So this is in the shape of a T. So this is Za, Zb and this is Zc. So now I am going to use the two-port method, which is this is a plus or minus V1, plus or minus V2, incoming current is I1 and the outgoing current is I1, incoming current is I2 and the outgoing current is I2. But here at this junction the incoming current is I1 and the incoming current is I2. So therefore overall outgoing current will be summation of two incoming currents, which is I1 plus I2. So now I am going to apply the KVL in this loop 1 and then I am going to apply the KVL in the second loop. If you apply the KVL in this first loop, we are going to get finally, which is V1 is equal to Za plus Zc into I1 plus Zc into I2. Similarly, if you apply the KVL in this loop, finally we are going to get V2 is equal to Zc into I1 plus Zb plus Zc into I2. So if you are going to write in terms of matrix form, which is V1, V2, I1, I2, which is Za plus Zc, Zc and Zb plus Zc. So you can compare with the standard Z parameter network, which is V11, V1, V2, Z11, Z12, Z21, Z22, I1, I2. So by comparing, we are going to get Z11 is equal to Za plus Zc, Z12 is equal to Zc, Z21 is equal to Zc, and Z22 is equal to Zp plus Zc. Therefore, Z11 is equal to Za plus Zc, Z12 is equal to Zc, Z21 is equal to Zc, and Z22 is equal to Zb plus Zc. Suppose if you want to convert in terms of, suppose in the sometimes the question they are going to give in terms of ABCD parameters, then how to get the value of the Za, Zb and Zc. So it's a very important formula you can remember, which is, suppose in the question sometimes they are going to give you ABCD parameters and then they are going to ask what is the value of Za, Zb and Zc. Then Za is equal to A minus 1 by C, Zb is equal to D minus 1 by C, and Zc is equal to 1 by C. So in the question sometimes they are going to give ABCD parameters and then they are going to ask what is the value of Za, Zb and Zc. So Za is equal to A minus 1 by C, Zb is equal to D minus 1 by C, and Zc is equal to 1 by C. So now we are going to find what is the Y parameter of the pi network. So you can see clearly this is in terms of pi fashion. So I want to find what is the Y parameter of this pi network we need to figure out. So you can see clearly here, this is in terms of the two-port network. So this is plus or minus V1, plus or minus V2, and this is incoming current is I1, outgoing current is I1, incoming current is I2, and outgoing current is I2. So now you can see clearly there are three principal nodes. This is the first principal node, second principal node, and third principal node. I am going to assume this is 0 a reference node. So its potential is 0. So this is V1 and this is V2. So therefore, if you apply the KCL at this junction, then we are going to get equation which is I1 is equal to Ya plus Yc into V1 plus minus Vc into V2. Similarly, if you apply the KCL across this junction, we are going to get finally, we are going to get this equation which is I2 is equal to minus Yc V1 plus Yv plus Yc into V2. So now I can write in terms of matrix fashion, which is I1, I2, V1, V2. This is Ya plus Yc minus Yc minus Yc, Yv plus Yc. So this is nothing but in the standard format of Y parameter, which is I1, I2, V1, V2, Y11, Y12, Y21 and Y22. So by comparing, we can tell that Y11 is equal to Ya plus Yc, Y12 is equal to minus Yc, and Y21 is equal to minus Yc, and Y22 is equal to Yv plus Yc. So if you know Ya, Yb, Yc, then you can easily get the value of all these parameters you can easily get. So now we are going to find the T parameter of the given circuit. So for the circuit, we are going to figure out the T parameter, or we are going to find the T parameter of this given circuit we need to figure out. So this is in terms of a two-port network, plus or minus V1, plus or minus V2. This is incoming current I1, this is also incoming current I2, this outgoing current is I1, and outgoing current is I2. So across this junction, two incoming currents are going to present, which is I1 and I2. So overall outgoing current is I1 plus I2. So now you can apply the KVL in this equation, and then you can apply the KVL in this equation. So finally you are going to get the equations which are V1 I1, V2 minus I2, which is 1 plus Za by Zb, Za 1 by Zb and 1. So these are the things that you are going to get, which is 1 plus Za by Zb, Za 1 by Zb and 1. So if you know this thing, it is very easy to remember this one. So 1 plus Za by Zb. The first term is Za, second term is 1 by Zb, the third term is 1. So this is the ABCD parameters. So by comparing with the standard ABCD parameters, which is V1 I1, V2 minus A2, A, B, C, D. So therefore A is equal to 1 plus ZA by ZB, B is equal to ZA, C is equal to 1 by ZB, and D is equal to 1. So now we are going to see about the series connection. Suppose when two port networks are connected in series manner, means suppose these two are connected in this fashion and these two parts are going to connect in this fashion, means if the overall input voltage is V1, it is going to split into two parts, which is V1A and V1B. Okay, this is called as a ZA matrix and this is a ZB matrix. So therefore now we can say that here the incoming current is same, this is I1, here also I1, same current is going to get flow. So we say that if the current is same, in these terms we are going to call it as a series connection, because in series connection the current will be same, so therefore we are going to say it as a series connection. Similarly, if the current is I2, same current is going to flow here also I2, here also same current I2. So we can say now these two we have to do this similar simplification, which is supply voltage is equal to V1A plus V1B. Similarly, V2 is equal to V2A plus V2B. So V2 is going to drop across this network and also this network. So by applying the Z parameter for the first network, we are going to get V1A, and also here we are going to get V2A is equal to ZA into I1 I2. Similarly, here if you are going to apply the Z parameter for second network, we are going to get V1B, and here it will be V2B is equal to ZB into I1 I2. But see, if you want the overall voltage, then you have to add these two vectors. So these two matrices you should add, then only you are going to get the overall input voltage, which is V1. Similarly, here V2A plus V2B is nothing but V2. So therefore you should add all these two matrices. Means if you add these two one, means you have to add this also. So therefore you are going to get common I1 I2, means you have to add these two matrices, which is ZA plus ZB. So therefore in series connection, definitely the overall Z net is equal to Z1 plus Z2, means you have to go for the addition of the Z parameters to get the overall Z parameter of the circuit. So whenever the two port networks are connected in series, we say that overall Z matrix is equal to summation of the individual Z parameter network. So now the circuit is simplified into a simplified version of V1, V2, I1, I2. So here incoming is I1, outgoing is I1, incoming is I2, and outgoing is I2. Where the overall Z parameter is the summation of individual, which is ZA plus ZB. So this is the overall Z parameter of this network, equivalent network. So now we are going to learn about the parallel connection. Parallel connection means voltage will be same. Suppose this is a YA network and this is a YB network. So therefore here this is the branch 1. So therefore these two branches are connected across this supply voltage V1, and these two branches are connected across supply voltage V2. So here also this is connected across the V1, and these two branches are also connected across the V2. So you can see clearly this is a V1 and this is I1. So this I1 is going to split into two parts, I1A and I1B. So I1A is going to come here, again it is going to come up here. Similarly, I2B is going to come here, and finally it is going to come here. So therefore this is again I1. Similarly, here V2, now the incoming current is I2 and the outgoing current is I2. So this current is going to split into two parts, I2A and I2B. And after that, this is going to come I2A and this is also I2B. So overall again current is I2. So therefore we can say simply the voltage across VA and VB is same for input side and also output side. So we say this is said to be parallel connection. So now I want to draw what is the equivalent network I need to figure out. So we can say I1 is equal to I1A plus I1B. Similarly, I2 is equal to I2A plus I2B. So now I am going to apply this Y parameter for the first network, which is A matrix, for the A port network, which is I1A, I2A. So therefore I1A, I2A is equal to YA into V1, V2. Similarly, for the second two port network also I am applying the same principle, which is I1B, I2B is equal to V1, V2, which is YB. So therefore this is the thing we are going to get. So if you want the overall current, you have to go for the addition of these two matrices, then only we can get the overall input current, which is I1 and I2. So we are going to get, if we add these two matrices, we are going to get I1 is equal to I1A plus I1B, so I2 is equal to I2A plus I2B, we are going to get, which is, we have to add these two matrices, then we are going to get V1, V2. So the overall Y parameter, whenever the two networks are connected in parallel, then overall Y parameter is equal to addition of the two individual Y parameters. So this is the equivalent circuit of I1 and I2, V1 and V2. So therefore we can say I1, I2 is equal to YA plus YB into V1, V2. So this is we are going to call it as the overall Y parameter. So whenever the two port networks are connected in series, means we have to add the Z parameter, and whenever the two port networks are connected in parallel, means we have to go for the addition of the Y parameters. Cascade connection means whenever the networks means output of one is connected as the input of the other network, then that fashion is called as a cascade connection. So output of this network is given as the input of this network, and similarly output of this network is given as input of this network. Then we say this is called as the cascade connection. So therefore, if this is V1 plus or minus V1, this is current is I1, and here plus or minus V2, incoming current is I2 and outgoing current is I2, then this will be equivalent to. So I am going to assume the ABCD parameters of the first network is TA, and the ABCD parameters of the second network is TB, and the ABCD parameters of the third network is TC. So whenever you are going to do the cascade, then the overall T parameter will be product of individual T port networks. So individual ABCD parameters. So therefore we can say overall ABCD parameters or T parameters is the product of individual network T parameters, which is TA into TB into TC. So this is the overall network matrix of plus or minus V1 plus or minus V2. Incoming is I1, outgoing is I1, incoming is I2 and outgoing is I2. So if you write in terms of ABCD parameters, which is V1 I1, V2 minus I2, which is TA into TB into TC. This is called as the overall ABCD parameter. So therefore, in the cascade connection, if you want overall T parameter, which is the multiplication of individual T parameters. So we have learned about the three, which is if the networks are connected in series, then definitely the overall Z parameter is equal to summation of the individual Z parameter. If the two port networks are connected in parallel means, then we can say overall Y parameter is equal to addition of individual Y parameters. But if the networks are connected in cascade means, the overall T parameter is the product of the individual T parameters. So we are going to learn some more important examples of Y parameters. So you can see here, this is the one network and this is the another network. So you can see clearly these two are parallel to each other. So this is a one network, Z2, Z3, Z4 are one network, and still only Z1 is of one network. So this is the meaning of Y parameter. Then you can apply Y parameter and you can get the overall Y parameter of this one. Similarly, here in this example also Z4, Z5, Z6 belongs to one parameter, and Z1, Z2 and Z3 are going to belong to another circuit. So you can find the Y1, Y2, and then if you want the overall Y parameter of the parallel network, which is the summation of the individual. So this is one example of T network. So this is one T network, this is another T network. So now these two are connected in cascade manner, means the output of one is given as the input of the other one. So then if you want the overall one, just go for the multiplication of this network and this network, then you are going to get the overall T network we are going to get. So now we are going to learn about the Z parameter of the lattice circuit. Now we are going to learn. See what is the Z parameter of the lattice circuit. So this is basically, we are going to call it as the lattice circuit. So for this circuit, we are going to find what is the value of the Z parameter we are going to figure out. So this is plus or minus V1, here is plus or minus V2. This is the current I1 and this is the current also I1. Here incoming current is I2 and outgoing current is I2. So here this is ZA, ZA. Similarly, this is ZB and ZB. So there is no touching point. These are non-intersecting points. So therefore you can say this is ZA, here also ZA. But here this is a ZB and ZB. So if these are connected in this manner, then what is the value of the overall Y parameter, which is V1? Then what is the value of the overall Z parameter we need to figure out, which is V1, V2, I1, I2. So this is nothing but here ZB plus ZA by 2. This is also ZB plus ZA by 2. But here ZB minus ZA by 2, ZB minus ZA by 2. So these two are same and these two are also same. So therefore ZB plus ZA by 2, ZB plus ZA by 2. Similarly these two are ZB minus ZA by 2. This is a ZB, this is also ZB, but this is a ZA. So it's an easy way to remember ZB plus ZA by 2. These are the two rows. These two elements are always equal, which is ZB plus ZA by 2, whereas these two elements are ZB minus ZA by 2. Whereas ZB are the diagonal elements, whereas ZA are the straight line elements. Now we are going to learn about the magnetically coupled circuits. Magnetically coupled circuits means, suppose there is a common iron bar, then on this we are going to round two coils. This is the coil 1 and this is the coil 2. So here dot indicates that from this point I am going to inject the current I1. Similarly for this coil also, at this point I am going to inject the current I2. Then if you apply your right hand thumb rule, if you curl your fingers, if you curl your right hand fingers in the direction of the current, and if the thumb indicates the direction of the flux. Similarly here also, if you keep your the right hand curl fingers in the direction of the current and the thumb indicates the direction of the flux. So you can see clearly these two fluxes are in the same direction. So therefore these two are connected in the series manner. So whenever the two currents are entering the dot or leaving the dot, always we say they are the added, series added, or we can say simply they are mutually seriously added. So therefore we can say simply these are the mutual flux are going, or we can say the flux are in the same direction. So therefore now you can do the, you can write in terms of coupling circuits. You can easily represent, which is here, this is L1 and this is, if then current is always goes from higher potential to lower potential. So this is plus minus, so this is also plus minus, but the mutual inductance is M into, here you have to go for the rate of change of this current, which is di2 by dt. Similarly here also, here because both are in same direction, so we can say this is L2, here also plus minus, here also plus minus, which is M into di1 by dt. So therefore V1 is equal to L into di1 by dt plus M into di2 by dt. Similarly V2 is equal to L2 into I2 di2 by dt plus M into di1 by dt. So this is the overall equation. Whenever two fluxes are in the same direction, then you go for the positive sign, otherwise you go for the negative sign. So here from the dot I am going to leave the current. So therefore what is going to happen? Here also from this dot also I am going to leave the current. What is going to happen? Now you curl your fingers in the direction of the current, then the thumb indicates direction of the flux. Similarly here, if you curl your fingers in the direction of the current, then thumb indicates direction of the flux. So there, let me assume this is a plus or minus V1 because I am going to inject the current in this direction, and also here also plus or minus V2, I injected the current in this direction. So therefore you can see still the fluxes are in the same direction, so overall flux is going to get added. Then you have to go for the V1 is equal to L into di1 by dt plus M into di2 by dt. So if you draw in terms of circuit diagram, so always current goes from plus to minus, here also plus to minus. So therefore we can say here this is L1, here this is plus M into di2 by dt. Similarly for this also, here this is I2 and here it will become L2 and here it will become plus or minus M into di1 by dt. So therefore V2 is equal to L2 into di2 by dt plus M into di1 by dt. So whenever the currents are going inject, or whenever the currents are entering the dot, or whether the currents are leaving the dot simultaneously, then we can say the overall flux is additive in polarity. Suppose I am going to inject the current in this direction, means the current is going to enter the dot, and if you curl your fingers in the direction of the current, you are going to get the flux in this direction. But here I am going to enter the current in this direction, so therefore the current is going to leave the dot. So you can see clearly, if you curl your fingers in the direction of the current, the thumb indicates the direction of the flux. So these phi 1 and phi 2 are opposite to each other. So therefore one is entering the dot and the other is leaving the dot. So therefore one is entering the dot and the other is leaving the dot, means the overall flux is negative. So therefore overall voltage drop is going to get decreased. So therefore then you have to go for here, you have to go minus plus. So therefore V1 is equal to L into di1 by dt minus of M into di2 by dt. So if you want to write in terms of diagram, you are going to get in this way, which is L1, here you have to go for the minus plus M into di2 by dt. Similarly here V2 is equal to L2 into di2 by dt minus M into di1 by dt. So if you write in terms of diagram, you are going to get same like this one, same as the previous one, which is L2, here M into di1 by dt, but here minus plus. Similarly here I am going to enter the current in this direction. So therefore if you curl your fingers in the direction of the current, we are going to get the flux in this direction. So here means the current is going to leave the dot, but here I am going to enter that dot, means I am going to make the current to enter the dot. Then if you curl your fingers in the direction of the current, you are going to get the flux. So you can see these two fluxes are opposite to each other. So here the current is going to leave the dot and here the current is going to enter the dot. So therefore we can see, so whenever these two fluxes are going to opposite to each other, so therefore overall voltage is going to get decreased, or overall flux is going to get decreased. So therefore we can say that overall voltage drop is also going to get decreased. So therefore now we can say here V1 is equal to L into L1 into di1 by dt minus M into di2 by dt. Similarly V2 is equal to L2 into di2 by dt minus M into di1 by dt. So if you want to draw in terms of this diagram, we are going to get this is L1, here go for the minus plus M into extra 2. Here also same thing, V2, here L2, and this will be minus M di1 by dt. So whenever the currents are entering the dot or leaving the dot simultaneously, then we can say overall flux is going to get increased. So whenever the overall current is going to increase, means whenever the overall flux is going to increase, means we can say simply that the voltage is also going to get increased. Then go for the positive sign. But if one is entering and other is leaving, means we can say that here the overall flux is going to get decreased, means the voltage is going to get decreased, then go for the minus sign. That's it. Now we are going to learn about the coefficient of coupling. See, suppose there is an iron core. On this core I am going to wound the two coils, coil 1 and coil 2. The coil 1 is going to have self-inductance of L1, whereas the coil 2 is going to have a self-inductance of L2. Then I am going to inject the current I1 in the coil 1 and I am going to inject the current I2 in the coil 2. Then because of this, there is a interaction of flux. Because of one coil, the flux is going to link the other coil. So this amount of useful flux that is going to link between these two coils, we are going to read with some symbol that is called as a mutual inductance. So this is called as a mutual inductance. So the M is called as a mutual inductance between the two coils. Then energy in both the coils. Then what is the energy in both the coils, which is half into L1 into I1 square plus half into L2 into I2 square plus or minus M into I1 I2. So plus we are going to say whenever the two fluxes are in the same direction, and go for the minus whenever the two fluxes are in the opposite direction. So therefore plus is used when phi1 and phi2 are in the same direction, minus you should use whenever the phi1 and phi2 are in the opposite direction. So this we are going to get the overall energy in the two coils, which is half into L1 into I1 square plus half into L2 into I2 square plus or minus M into I1 I2. Where plus is used when the two fluxes are in the same direction, and minus means when the two fluxes are in the opposite direction. The coefficient of coupling is equal to ratio of mutual inductance by under root over product of two self-inductance, which is K is equal to M by under root over L1 into L2. K is equal to M by under root over L1 into L2. When K is equal to 0, we say M is equal to 0. So therefore these are isolated coils, means there is no intersection or there is no common area, or we can simply there is no these two are no way related. So therefore we can say when K is equal to 0 means M is equal to 0. When K is equal to 1 means M is equal to under root over L1 L2, means tightly coupled coils, means all the useful flux is going to get interact between the two coils. Then we say then only K is equal to 1. So therefore K is equal to 0 means isolated coils, K is equal to 1 means tightly coupled coils. So therefore always K can lie between only 0 to 1. So therefore if K is going to lie between 0 to 1, means M can go from 0 to under root over L1 L2. So therefore M can lie from 0 to under root over L1 L2. So therefore this is the way. When K is equal to 0, M is equal to 0, K is equal to 1, M is equal to under root over L1 L2. So therefore when K lies from 0 to 1, definitely M is going to lie from 0 to under root over L1 L2. When K is equal to 0, we say it as a isolated coils. When K is equal to 1, we are going to say it as a tightly coupled coils. So now we are going to learn about the series connection, means series shading. Series shading means here in a common iron bar we are going to wound two coils. We are going to wound the two coils and we are going to connect in a series manner, means the current is same in both the coils. Then here M is the mutual inductance between the coil 1 and the coil 2, and you can see clearly here in the first coil the current is going to enter the dot, and in the second coil also the current is going to enter the dot. See, in the two coils in the same dot, if the current is going to enter means the fluxes are L2. So therefore we can say here, we can say that here V1 is equal to L1. This voltage V1 is equal to L1 into, here we can say V1 is equal to L1 into di by dt plus M into di by dt, because here also the current is same. So therefore here similarly V2 is equal to L2 into di by dt plus M into di by dt. So if you apply by KVL rule, V is equal to V1 plus V2, by using that property, finally we are going to get, if you want to find what is the overall inductance, which is equal to L1 plus L2 plus 2M, because it is a series aiding, because the current is entering both the dot terminals. So we can say the equivalent inductance is equal to L1 plus L2 plus 2M. So now we are going to learn about the series opposition, means the two coils are going to connect in series, but in one coil the current is entering the dot, but in the other coil the current is leaving the dot. So therefore we can say these two are oppositely series opposition, means the flux of one direction is opposite to the flux of the other coil. So because of that we say it is a series opposition. Then if you want to know what is the overall inductance, where M is the mutual inductance between the coil 1 and coil 2, so if you want to know what is the overall inductance of this coil, which is equal to L1 plus L2 minus 2M. This is the equivalent circuit. So therefore this is the L equivalent, this is the I, and this is the V. So therefore we are going to get L equivalent is equal to L1 plus L2 minus 2M. So therefore whenever series adding means the equivalent inductance is equal to L1 plus L2 plus 2M, but whenever the two are connected in the series opposition, the equivalent inductance is equal to L1 plus L2 minus 2M. So now we are going to learn about the parallel connection. So in the parallel connection we are going to learn about the two things, parallel aiding and the parallel opposing. See, parallel aiding means the two coils are connected in a parallel fashion means voltage across them is same, but they are going to do a aiding process means the current is going to enter in L1 and similarly the current is also going to enter in the L1. Then we say it is called as a parallel aiding. Then where M is the mutual inductance between the coil 1 and coil 2. Then I want to find what is the overall inductance I need to figure out. So therefore this is the overall inductance circuit. L equivalent is equal to L1 L2 minus M square by L1 plus L2 minus 2M. So we can see clearly in parallel aiding the equivalent inductance is equal to L1 L2 minus M square by L1 plus L2 minus 2M. In the parallel opposing means here these two coils are connected in parallel where M is the mutual inductance between L1 and L2, but here the coil 1 the current is going to enter the dot, but in the coil L2 the current is going to leave the dot. So because of that we are going to say it as a parallel opposing means the flux are opposite to each other. Then if you want to know what is the overall equivalent inductance which is equal to L1 L2 minus M square by L1 plus L2 plus 2M. See here the denominator is higher than the previous one. As the denominator is higher, so we can say the overall value is lesser. So that is the reason in parallel opposing this is lesser than the previous one. So therefore L equivalent is equal to in the first one in the parallel adding which is L equivalent is equal to L1 L2 minus M square by L1 plus L2 minus 2M, whereas here L equivalent is equal to L1 L2 minus M square by L1 plus L2 plus 2M. So now transformer T equivalent circuit. So this is basically a transformer. Now I am going to convert into T equivalent circuit I am going to figure out. See here this is the transformer of primary coil and the secondary coil, where L1 is the self-inductance of the primary coil and L2 is the self-inductance of the secondary coil, where here there is an extra parameter M. M is called as the mutual inductance between the coil L1 and coil L2. So you can see clearly that M is the mutual inductance between the primary coil and the secondary coil. Here I am going to assume the current is entering and here also the current is going to get entering. So now if you apply that, this is called where both are in the, or you can say both are going to enter. So therefore we can say overall voltage is going to get increased. So if you apply the KVL in the first loop and also the second loop, then we can draw the equivalent circuit like this, which is L1 minus M, L2 minus M and M here. Same plus or minus V1 plus or minus V2, current I1, current I2. So if you write the KVL for this loop and KVL for this loop, it is equal to KVL in this loop and also equal to KVL in this loop. So therefore this is the equivalent diagram, which is L1 minus M, here M, L2 minus M, V1, V2 plus or minus I1, here also I1 is leaving, here I2, here also I2 is leaving. But if they are opposite, so therefore one is going to enter but the other is now going to leave, then just replace minus M by minus M. You are going to get L1 plus M, L2 plus M and minus M, and everything is same. So therefore this is the only thing that you need to remember. So therefore the KVL in this loop is equal to KVL in this loop, so the KVL in this loop is equal to KVL in this loop. So therefore here this is L1 minus M, L2 minus M and this is M. When the current is going to enter the dot terminals in the both ways. But if one is entering and the other is leaving, means just replace plus M by minus M, we are going to get here L1 plus M, L2 plus M and here minus M, and remaining everything is same. So instead of doing the analysis of this circuit, you can go for the analysis of this circuit in a very easier manner. So now we are going to analyze this given circuit. Suppose there is a like this primary coil and secondary coil, where like a transformer, which is L1 is the self-inductance of the primary coil and L2 is the self-inductance of the secondary coil, where M is the mutual inductance between the primary coil and the secondary coil, and this is voltage V1 and this voltage is V2, and this entering current is I1 and entering current is I2. So you can see clearly that both the currents are going to enter, so therefore there is a additive. So because of that we can say now we can apply the KVL in the first loop and the KVL in the second loop. So therefore here V1 is equal to L1 into dI1 by dt plus M into dI2 by dt. Similarly V2 is equal to L2 into dI2 by dt plus M into dI2 by dI1 by dt. So if you write the KVL like this, we are going to get finally, so we are going to get KVL in this manner, which is here if you rearrange this one, we are going to get finally V1 is equal to L1 into dI1 by dt plus M into dI2 by dt. Similarly V2 is equal to M into dI1 by dt plus L2 into dI2 by dt. Or simply we can write, see here if you apply the KVL from minus to plus, it is plus V1, but plus to minus means minus, but it is going to, the voltage drop is going to get increased, which is L1 into dI1 by dt plus M into dI2 by dt is equal to 0. So if you rearrange this one, we are going to get this expression. Similarly here, if you apply the KVL in the secondary loop, we are going to get plus V2 minus of, here because of series, we can say aiding property, overall voltage drop will increase, which is plus. So L2 into di2 by dt plus M into dN by dt is equal to 0. So if we are in this one, we are going to get V2 is equal to M into di1 by dt plus L2 into di2 by dt. So now here I am going to write these two equations in terms of matrices, which is V1 V2 di1 by dt di2 by dt. So we are going to get L1 M L2. So we are going to get the overall matrix, which is L1 M L2. So this I am going to call as some matrix of L, which is L1 M L2. It's a very important thing here. So here these are some of the important formulas here. Suppose there are two branches. The first branch is of R1 L, R2 and C. So we are going to connect across a voltage source. Then if you want to know what is the resonant frequency equation, which is omega naught is equal to 1 by under root over LC into under root over R1 square minus L by C by R2 square minus L by C. So this is the equation is going to hold only when R1 square is not equal to L by C and R2 square is not equal to L by C. So we can say this is called as the resonant frequency. At this resonant frequency, the circuit will be purely resistive. So omega naught is equal to 1 by under root over LC into under root over R1 square minus L by C by R2 square minus L by C, when R1 square is not equal to L by C and R2 square is not equal to L by C. We know this called as the resonant frequency. Suppose there is a parallel RC circuit. So when I am going to apply a voltage of V across this parallel RC circuit, then I can say that the power is going to last only across the resistor but not across C. So P is equal to V square by R. So this is called as the power loss across the resistor. And if you want to know what is the dissipation factor, the dissipation factor is tan delta, which is equal to Xc by R, which is equal to Xc by R. So Xc is 1 by omega C by R, which is 1 by omega CR. So this is the dissipation factor, which is Xc by R. So therefore tan delta is also called as a dissipation factor, which is Xc by R is equal to 1 by omega RC. So there is a LC parallel circuit. So LC parallel circuit. So if you want to know what is the overall impedance of this circuit, which is here, you can write which is JXL means J omega L, and this is minus JXC means minus J by omega C. So if you do the Z1 Z2 by Z1 plus Z2, finally you are going to get Z is equal to J omega L by 1 minus omega square LC. So if you are going to find only the magnitude part of the impedance, means take only the magnitude part, which is omega L by 1 minus omega square LC. So now we can say that here, what is the resonant frequency? The resonant frequency is called as the omega naught is equal to 1 by under root over LC. So if omega naught is equal to 1 by under root over LC, we can definitely say that if you substitute in this equation, we are going to get denominator as 0. So therefore overall value will become infinity. So therefore mod Z is equal to infinity. So this is the thing that you need to remember here. When omega naught is equal to 1 by under root over LC, we are going to get an impedance of infinity. When suppose if omega naught is lesser than 1 by under root over LC, then what is going to happen? This 1 minus omega square LC will be positive. So therefore we can say that it's a positive indicates that its overall value is positive. So therefore this will be a inductive in nature. But then omega naught, when the omega is greater than omega naught, what is going to happen? This overall value will become negative. Means 1 minus omega square LC value will become negative, means this overall value will become negative. So therefore we can simply say that this is a capacitive in nature. This will be a capacitive in nature. But here this for omega naught, for omega less than omega naught, this overall value is positive. So this is a positive in nature. But when omega is greater than omega naught, this overall value will become negative. So that's why it is down in nature. So we can say the magnitude of the impedance can be positive, can be negative. So at omega naught it is infinity, but when omega is less than omega naught, I have told you it is an inductive circuit because the magnitude of Z is a positive value. But here for when omega is greater than omega naught, still the magnitude of Z values become now negative value. So because of that it will be a capacitive in nature. So this will be like, this is the graph we are going to get. As omega is very high, we are going to get the ratio will become tends to 0. Similarly, if the omega is very less, still also we are going to get that it's going to become 0. Suppose there is a one more like same branches, like first branch of RC and second branch of RL. Means we can say both the resistors are same value. Only thing is RC and RL. We are going to apply some external voltage source. Then when R is equal to under root over L by C, suppose when R is equal to under root over L by C, then circuit is said to be purely resistive for any frequency. See, no matter whatever the frequency we are going to apply, the circuit will be always will be always a purely resistive circuit, or we can say purely supply voltage and supply current will be always in phase no matter whatever the frequency of the supply. So therefore when R is equal to under root over L by C, definitely the circuit is always resistive no matter whatever the supply frequency. So now we are going to learn about the graph theory. So some of the basics in the graph theory are: a network topology is the study of the network properties by investigating interconnections between the branches and the nodes. It mainly concentrates on geometry of the network. So basically this network topology we are going to call it as the study of the network properties by investigating interconnections between the branches and the nodes. So we are going to study the nature of the branches and the nodes, how they are going to interconnect, and this is basically about the concentration or the geometry of the network. So in the network topology, any network can be replaced by graph. So with the help of network topology, any network can be replaced by graph. To develop the graph, each element is replaced by either straight line or arc of the semicircle. Means here each and every element we are going to replace by a straight line or an arc of a semicircle. So voltage source is replaced by short circuit, whereas the current source is replaced by open circuit, and the graph retains all the nodes of the original network. So basically here we are going to represent each and every branch or each and every element by a straight line or a semicircle, and also here if there are voltage sources then we are going to short circuit them. If there are current sources means we are going to open circuit them. And also this graph is going to contain each and every all the number of nodes which are going to present in the original network. So from the graph we are going, from the network we are going to draw the graph. So in the network topology, any network can be replaced by graph. To develop the graph, each element is replaced by either straight line or arc of the semicircle. Voltage source is replaced by short circuit, whereas the current source is replaced by open circuit, and the graph retains all the nodes of the original network. And the number of branches of the actual network drawn is always greater than or equal to the number of branches of the graph drawn. So what is going to happen is, as we are going to remove the current sources, so because of that there may be some branches are gone out. So therefore that is the reason we can say the number of branches of the actual network drawn are always greater than or equal to the number of branches of the graph drawn. So now we are going to learn about the augmented or the complex incidence matrix. So this is called as the augmented or the complex incidence matrix, which is represented by a capital A with a subscript of A. So we are going to call this as the augmented or complex incidence matrix. So basically it is going to have like this. So basically it is a matrix. So this we are going to say the number of rows is equal to the number of nodes. Means the number of nodes in this matrix is nothing but here it is equal to the number of nodes. So and this is called as the branches. So this number of columns is equal to branches, and the number of nodes is equal to is called as the number of rows. So therefore here the number of nodes cross number of branches. Means if you want to know what is the order of the matrix, which is nodes cross branches. See, the current inside the node I am going to take it as negative, and the current outside node I am going to take as a positive. If current not assigned with any node, I am going to represent as 0. So therefore here I can assume this is just a normal convention, which is the current inside node I am going to assume it as -1, and the current outside node is nothing but +1. Then the current which is not going to assign with that node we are going to assume as 0. So basically these are the nodes. So now for these nodes I am going to see how many branches are going to get intersect, and then if the current is inside that node we are going to say that it is a positive. Otherwise if you are going outside it is, see I am assuming that if the current is outside that node I am going to assume as positive, and if the current is inside that node I am going to assume as negative with respect to that node. And if any branch is not going to intersect at that node, we are going to assume as 0. So by this way we have to fill each and every row, then we are going to get certain matrix. That matrix is going to give you information that at what node how many numbers are going to intersect, and also what is the direction of the current also in the branch we can all know from this graph itself. So from this diagram we know that here the number of rows is equal to the number of nodes, and the number of columns is equal to number of branches. So at each and every node we have to see, at each and every node we have to say how many numbers are now, how many number of nodes, how many number of branches are going to intersect at that node, and we have to assume that if any current outside that branch in that node we are going to assume as positive, and the current inside that node is negative. If some branches are not going to intersect that node means assume it as 0. So this is the way that you need to fill each and every row, then you are going to get a certain matrix. That matrix we are going to call it as the augmented or the complex incidence matrix. all the information regarding the graph can be represented mathematically in concise form is called as the augmented incidence matrix. So all the information regarding the graph can be represented mathematically in concise form is called as augmented incidence matrix. So with the help of augmented incidence matrix, you are able to know at what node how many number of branches are going to get intersect, and also you can know what is the direction of the current in that branch also you can easily know. So this is called as you can know the exact information of the original network from the graph with the help of this augmented incidence matrix. See, for the given graph, augmented incidence matrix is unique. So therefore here, if you take one graph for a given network, then the augmented incidence matrix, whatever the thing that you are going to get is a unique in nature. In the augmented incidence matrix, sum of each column is 0. So always sum of each column is always equal to 0 for augmented incidence matrix. Means if you take all these columns, then if you do the addition of all the columns, you are going to get 0. This is because of the KCL. So this is we are going to get with the help of KCL, because sum of all incoming currents is equal to 0, or we can say we are going to assume all are incoming. So therefore net algebraic sum of current which is going outside any particular node is equal to 0. So with the help of that equation we are going to get here that sum of each column is definitely equal to 0. Determinant of augmented incidence matrix of the closed loop is equal to 0. So the determinant of the augmented incidence matrix of the closed loop is equal to 0. So if you figure out the determinant of this augmented incidence matrix, then definitely you are going to get as equal to 0. Network topology is applied only for planar networks. See here we have to apply this network topology only for the planar networks, but not for the non-planar networks. See, mesh analysis is applied only for planar networks but not for the non-planar. So you can see clearly here this network topology is applied only for the planar but not for the non-planar networks. By treating any one row as a reference node and removing it from the augmented matrix is called as a reduced incidence matrix, which is symbol as A, capital A. So therefore we can say clearly here, see, out of all the nodes I am going to assume one node as a reference node, and if you remove that row from the augmented incidence matrix, then the new reduced matrix is also called as the reduced incidence matrix. Means whatever the matrix you are going to get in a new, that we are going to call it as a reduced incidence matrix, and the symbol of that matrix is capital A. So now we are going to learn about the concept of tree. Tree is a connected subgraph. It connects all the nodes of the network, but it does not contain any closed path. See, basically here, suppose from the original network you have drawn some graph. So basically tree is nothing but it is going to contain each and every node of the original graph, but there will be no closed paths. That is the only difference. So therefore we can say tree is a connected subgraph. It connects all the nodes of the network, but it doesn't contain any closed path. Means it is going to contain all the nodes of the original graph, but there will be no closed paths. A set of branches which are disconnected to form a tree is called as the complementary tree or core tree or chords or links. So here there are some branches. So in a tree there will be some branches that we are going to call it as a tree, but there are few branches which are not going to connect to that tree. That branches we are going to call it as the complementary tree or core tree or chords or links. So these are the different names for that. So therefore the set of branches which are disconnected to form a tree, these are called as the complementary tree or core tree or the chords or the links. You can name any of these things. The branch which form a tree is called as a tree branch or twig. See, the branches which are helpful to make a tree are called as the tree branch or twigs. Number of tree branches or twigs is equal to n minus 1. So therefore here, if you want to know how many number of tree branches or twigs are present in a given tree graph, so we are going to call it as it is equal to n minus 1, where n is equal to all nodes in the graph including the reference node. Here n is called as that you have to include each and every node present in that original graph. So therefore we can say it is going to include even the reference node. So we can say simply here the number of twigs is equal to n minus 1, where n is called as the number of total nodes present in the given graph. It is always, then we have to even include the reference node also. The branch which is disconnected to form a tree is called as links. I have already told you the branches which are disconnected to form a tree are called as the complementary tree or links or chords, or it is also called as the links. So now if you want to know the relation between the number of links and the number of branches and the number of twigs, which is the total number of branches is equal to the total number of branches is equal to the number of links plus the number of peaks. This is the basic relation. So therefore, the total number of branches in a given graph is equal to total number of links plus total number of peaks. So if you want only links, then go for the subtraction of total number of branches minus total number of peaks. So therefore, the total number of links is equal to total number of branches minus total number of peaks, which is n minus 1. So therefore, L is equal to b minus of n minus 1. So by this way, you are going to get the relation between the number of links, the total number of branches, and also the total number of peaks. So B is called as the number of branches of the network drawn on graph. See, this is called as the total number of branches of network drawn on a given graph. So from the original network, we are going to draw the graph. So how many number of branches which are going to present on the graph, we are going to represent by a symbol of B. Whereas capital N indicates the number of all nodes of the network. It is going to include even the reference node. So therefore, it is going to contain each and every node present in that graph. Always there has to be interconnection between the three branches of the graph. Always there has to be interconnection between the three branches of the graph. Means we can say that here always there will be nothing like isolation. Means even if one node cannot be isolated, all things are going to interconnected. Means all the nodes should be interconnected. There will be nothing like isolation. So that is the reason always there has to be interconnection between the three branches of the network. The total number of possible trees is equal to, here suppose if the graph has n number of nodes, total number of nodes are n, then we can say that the number of possible trees we can obtain is equal to capital N to the power of capital N minus 2. So therefore, n to the power of n minus 2, this many number of trees we can obtain with the help of n number of nodes. So therefore, n to the power of n minus 2, this formula is valid only when the connection is present between all the nodes and also no repeated branches present between the nodes. So these are the two conditions must be satisfied in order to hold this formula, which is the total number of trees possible for n number of nodes is equal to n to the power of n minus 2, where n is called as the total number of nodes present in that graph. Here this formula is going to be valid only when connection is present between all the nodes, means all the nodes are interconnected. There is nothing like isolated node, and also see there has to be only one branch between the two nodes. See, there must not be more than one between two nodes. There must not be more than two branches. That is the condition. Means only one branch should be there between two particular nodes. If these conditions are satisfied, then only we can use this formula, which is the total number of trees for a n number of nodes is equal to n to the power of n minus 2. The total number of possible trees for any network is modulus of the A into A transpose. Means it is called as the determinant of the A into A transpose. If you find the determinant of this A into A transpose, then you are going to get some numerical value. So therefore, you can go for any of this formula, which is n to the power of n minus 2 or determinant of the A into A transpose. Both are going to give you same number of results. So therefore, the total number of possible trees for a n number of node is equal to the determinant of A into A transpose or n to the power of n minus 2, where A is called as a reduced incidence matrix. This is a matrix of reduced incidence matrix. But this formula won't have any limitations, so blindly use it for any graph. So therefore, this formula doesn't have any limitations. You can apply for any graph, you are going to get the result. But the previous one has that two limitations that I have already told you. Number of node pair voltages for any graph is, see, the number of node pair voltages for any graph is, it is equal to NC2. Means you want to know how many number of node pair voltages. Means out of n number of nodes, you want to pair two things. So therefore, you can take for NC2 combinations, which is n into n minus 1 by 2. So this by number of node pair voltages we can get. And number of edges or branches is equal to, basically number of branches means between 2 points, between two nodes we can get one branch. So therefore, NC2, out of n number of points we have to select 2 points in order to get one branch. So therefore, number of edges or branches is equal to NCT is equal to n into n minus 1 by 2. This formula is valid only when connection is present between all the nodes and no repeated branch is present between the nodes. This is the same as the previous concept, which is here at least one branch should be present between only one branch should be present between two particular nodes, and there should not be no isolated nodes. If above two statements are satisfied, then it is said to be a fundamental graph or the complete graph. See here, the fundamental graph or complete graph means simply the basic rule is here, there should not be any isolated node, and there should be at least, there should be only one branch between the two particular nodes. If these conditions are satisfied, whatever the graph we are going to get, it is called as the fundamental graph or the complete graph. Number of branches associated at the node is called as the degree of the node. See, the number of branches associated at the node is called as the degree of the node. Suppose if you want to know what is the degree of the node, means at that node how many number of branches are connected, that is going to call as the degree of the node. See, the number of branches connected across any particular node, we are going to call it as the degree of the node. So degree of the node means how many number of branches are connected at that node. That is going to give you the information of the degree of the node. If degree of all the nodes are equal, then it is said to be a regular path. Means if for each and every node, if the degree of the node is same, then we can say it is a regular graph. Means for each and every node, equal number of branches are going to get intersect, then we are going to call it as the regular graph. When each node is connected to at least one branch, then it is called as the connected graph. When each node is connected to at least one branch, then it is called as a connected graph. Means there is nothing like any node is isolated, then we can say it is a connected graph, because each node is connected to at least one node or at least one branch. So because of that reason, we can say that it is a connected graph. When one of the node is not connected to any one of the branch, then it is said to be isolated graph. Isolated graph means at least one node is not connected to any of the branch, then we are going to call that is a isolated graph. So now we are going to learn the concept of procedure for the fundamental tie-set matrix. Fundamental tie-set matrix. See, in order to make the fundamental tie-set matrix, the first thing is you have to develop a tree for a given graph. So for a given graph, you should always make a tree. That is the first concept. So you have to develop a tree for a given graph. Identify total number of basic loops or fundamental loops or F loops or independent loops. So therefore now here first thing is from the graph you have to make a number of trees, or we can say you have to develop a tree from a given graph. Then identify total number of basic loops or fundamental loops or F loops or independent loops. How many loops you can make with the help of this tree, you need to figure out. So the number of loops is equal to the number of links, or we can say the complementary tree branches, that is equal to the number of basic loops. So basic loops should consist of only one link. So if you are going to make any closed path, then the closed path should have only one link, and the remaining branches of that loop should be always twigs. That is the meaning of the basic loops. So basic loop should contain only one link, and the remaining branches of that loop are said to be twigs. So the total number of basic loops is equal to the number of links in the given graph, so in the given tree diagram. So therefore is equal to total number of branches minus the total number of links, which is the total number of twigs, which is b minus of n minus 1. So this by number of basic loops you can get with the help of that given graph. The basic loop direction is same as the link current direction. So therefore here for that given loop you should take the direction of that loop is equal to the direction of the current in that link. So therefore that is the direction you should always choose. In the fundamental tie-set matrix, link current form an independent set. So therefore here in the fundamental tie-set matrix, so with the help of this we are going to make a fundamental tie-set matrix. Then link current is going to form an independent set. Now we are going to learn why it is going to make an independent set. So here this is C is called as the fundamental tie-set matrix. So this is basically a tie-set matrix or fundamental tie-set matrix. So you can see clearly here the number of rows is equal to the number of links. So therefore this is called as the number of links. So these are the number of links. So these are I am going to represent these rows as link currents. These are the link currents, and the number of columns is equal to the number of branches. So because of that, the order of this fundamental tie-set matrix is equal to the number of links cross of the total number of branches. So therefore here the number of rows are the link currents, and this is called as the number of branches. So with the help of branches you can get the branch voltages also. So for each and every branch you are going to assume some voltage. So with the help of that you are going to get the branch voltages, and also for each and every branch you are going to get the branch currents also. So therefore for branches you can consider the branch voltages and also the branch currents. So to all those branches in fundamental loop which are in the direction of link current, otherwise not. So assign +1 to all those branches. Assign +1 to all those branches in fundamental loop which are in the direction of the link current, otherwise not. Means here you have to make that basic loop, and whichever the currents are in the direction of the link current, assign them as positive, otherwise negative. If nothing is there, then assume it as 0. Then here you can see for this link current. So for this link current, how many branches are going to peaks are going to present? Here, if they are in the same direction, take it positive. Otherwise, if they are in the negative direction, assume it is negative. If there is nothing branch is intersecting with that link, then assume it as 0. So by this procedure, fill each and every row. So by this procedure, you can fill each and every row. You are going to get the sub matrix. That matrix you are going to call it as a fundamental Dissect matrix. So for each row of the C matrix, write KVL and equate it to 0. So see, for each row of the C matrix, write KVL and equate it to 0. Means here we are going to, basically what we are going to do is, we are going to write the KVL for each and every row. Means like it's like a equation of branch voltages. So with the help of this, we are going to get the KVL of each and every loop you are going to get. So therefore, you will get KVL equations for all the fundamental loops. So therefore, we can say clearly. So with the help of this, if you are going to see for each row of the C matrix, write KVL equations and equal to 0. So therefore, you are going to get the branch voltages. Means the summation of branch voltages in the closed loop is equal to 0. So therefore, you are going to get the KVL equations for all fundamental loops you are going to get. So now, suppose for that equation, means you got all the fundamental loops KVL equations. So now you can write in this format, which is C matrix into VB is equal to 0. This is basically a matrix. So all those equations you can write in terms of this matrix, which is C into VB is equal to 0. All these are the matrices. So therefore, VB means these all are branch voltages, V1, V2 up to VB. The total number of branches represent VB. So therefore, like this you can get. So these are basically branch voltages, and this C is called as the fundamental Dissect matrix you are going to get. So therefore, this is a way that C into VB is equal to 0. So this is the equation you are going to get. Relate all branch currents with link currents, and we will get it's like a basically KCL. Now we are going to apply the KCL at each and every node. So we are going to get the relation between the link currents and the twig currents. So therefore, we can say that here relate all branch currents with the link currents, and we will get going to relate all the branch currents and the link currents. Then you are going to get some certain equations. It's like a KCL. Then if you can write in this that equations in terms of this matrices, which is IB is equal to C transpose into IL. So therefore, the relation of branch currents is equal to C transpose into link currents. So by this you are going to get the KCL for each and every node you are going to get. Dissect matrix is not unique because here with the original network you can draw so many number of graphs. If the graphs are so many, then for each and every graph you are going to get a different Dissect matrix. So because of that reason only we say Dissect matrix is not unique, and in this unique matrix may or may not possible. Sometimes a unique matrix may be possible, and sometimes a unit matrix may not be possible. Sometimes unit matrix may be possible, and sometimes unit matrix may not be possible when you are going to figure out the matrix C. So therefore, sometimes you can get the unit matrix like this fashion. The C matrix you can write into two matrices of unit matrix, and also this is CB. You are going to call U as the unit matrix, where C is called as the fundamental Dissect matrix. Sometimes unit matrix may be possible, but sometimes unit matrix may not be possible. So therefore, C matrix you can divide into two parts: unit matrix and non-unit matrix. So therefore, U is called as unit matrix and C is called as the fundamental Dissect matrix. So by this way, we can figure out the Dissect matrix. So now we are going to discuss about the procedure for the fundamental Cascade matrix. So this is the last concept here. The procedure for the fundamental Cascade matrix now we are going to learn. See, develop a tree for a given graph. The first thing is, first you have to develop a tree for a given graph. Means from original network draw the graph, and from the graph take one tree. So therefore you have to make a tree from a given graph. Then identify total number of basic Cascades or fundamental Cascades or F Cascades. Then here the number of Cascades or fundamental Cascades or F Cascades, it is nothing but the number of nodes. So the number of nodes, or you can say the number of nodes is equal to the number of Cascades, or simply we can say the number of twigs is equal to the number of Cascades. Cut at each node in such a way only one twig or tree branch present, and the direction of basic Cascade is in the same as the tree branch direction. The number of basic Cascade is equal to the number of twigs. So therefore, cut at each node in such a way only one tweak or tree branch present. Means you have to, at each and every node you need to cut only one tree. So therefore here you can see clearly that the number of tree branches is equal to the number of cut sets. So therefore cut at each node in such a way only one tweak or tree branch present, and the direction of the basic cut set is in the same direction as the tree branch direction. Basic cut set should consist of only one tree branch. So therefore I have already told you that basic cut set should contain only one tree branch, and the direction of that cut set is in the direction of the current in the tree branch. The total number of basic cut sets is equal to the total number of tree branches, which is equal to n minus 1. So the total number of basic cut sets is equal to the total number of tree branches, which is equal to n minus 1. So basic cut set direction is in the same as the tree branch current direction. This point also I have already told you, which is the basic cut set direction is in the same as the tree branch current direction. So in the fundamental cut set matrix, branch voltages forming an independent set, whereas in the fundamental tie set matrix I have already told you that link currents are going to form an independent set, whereas in the fundamental cut set matrix the branch voltages are going to form an independent set. So now this B is called as the fundamental cut set matrix B. So here the number of rows is equal to number of tweaks. So the number of tweaks is called as the number of rows, and the number of columns is equal to the number of branches. So therefore here we are going to call it as the tree currents, or the number of tree currents is equal to the number of trees. So therefore here we are going to assign the node voltage is current. So now these are the tree branches, and this is also called as the node voltages corresponding. So therefore for each and every tree branch, or we can say node, there will be a corresponding node voltages. So therefore this is also we can assign. So here the number of branches, or you can go for the branch voltages and also branch currents. So you can go for each and everything here. So therefore we can say the order of this matrix is equal to the number of tweaks cross the number of branches, where B is equal to, so you can split the matrix B into two parts, which are, it may have some unit matrix and there may be a non-unit matrix. So order of this matrix is the number of tweaks cross the number of branches. So now relate branch currents at that node. So relate branch currents at that node. Now write these in matrix form we get. So here write the KCL equations at each and every node. Then we are going to, so we can write that in terms of matrix form also, which is matrix B into IB is equal to 0. So therefore relate branch currents at that node. Now write them in the form of matrix form. Means you have to write the KCL equations at each and every node, and you can write in terms of this matrix also, which is B into IB is equal to 0. So matrix cut set matrix B into IB is equal to 0, where IB is the branch currents. So now relate branch voltages with the node voltages. So with the help of node voltages we can figure out the branch voltages also, and write in a matrix form we get, which is branch voltages is equal to B transform into node voltages. So this also we can get with the help of the fundamental cut set matrix. So therefore branch voltage is equal to B transpose into Vn, where branch voltages are going to form the independent set in the fundamental cut set matrix, whereas the link currents are going to form the fundamental, or we can say independent things in the terms of the fundamental tie set matrix. So now we are going to learn about the relation between the tie set matrix and the cut set matrix. Tie set matrix means simply, see, the relation is C, and the cut set matrix means we are going to go for the matrix of B. So therefore C means it is a tie set matrix or fundamental loop matrix, whereas B means cut set matrix. I have already told you the C matrix, sometimes there may be a unit matrix, or see, for the cut set matrix I have already told you there may be some unit matrix, or see, now we are going to learn about the relation between the tie set matrix and the cut set matrix. So you can see clearly the first concept I told you about. So now we are going to learn about the relation between the tie set matrix and also the cut set matrix. So I have told you in detail about the tie set matrix and also the cut set matrix. Here C matrix I have already told you, this is called the tie set matrix or the fundamental loop matrix, whereas the B is called as the cut set matrix. So this is C means tie set matrix or fundamental loop matrix, and B means cut set matrix. So I have already told you C is nothing but it may have or it may not have the unit matrix, so therefore UCB, whereas B matrix I am going to split into two parts. It is going to contain UT matrix and also BN. So if you know one thing, you can get the remaining matrix. The relation between the tie set matrix and the cut set matrix is here. See, if you want to know what is the value of CB, CB is equal to minus BL transpose. So therefore here this is tie set matrix, which is CB is equal to minus BL transpose. So therefore if you do the transpose of this Cascade matrix of this component, you are going to get the value of the CB. So if you know this thing, the remaining is the unity matrix. So you can easily go for this one. So therefore, with the help of this relation, which is here CB is equal to minus BL whole transpose, you are going to convert from one domain to the other domain. Or if you know Cascade, you can use this formula to get the value of the Dissect, and if you know Dissect, you can use this formula to get the value of the Cascade. So the reverse process also, which is BL is equal to minus CB transpose. So you can use any of this formula, you are going to get the same result. These are some of the important formulas of the graph theory, which are the here n indicates the total number of nodes, means it is going to include even the principal node. So therefore it is going to include each and every node present in the graph. Here B is called as the total branches, it is equal to NC2. This condition is going to apply only when there is only one branch within two nodes. So by then we are going to get the total branches is equal to NC2, where L is called as the total number of links. It is equal to, always you have to remember, which is the total number of links plus the total number of trees is equal to total number of peaks is equal to total number of branches. So the total number of possible trees is equal to n to the power of n minus 2 or determinant of A into A transpose. I have already told you these two important formulas. So here from a given graph, the number of possible trees are n to the power of n minus 2 or determinant of A into A transpose, where A is called as the reduced incidence matrix. Dissect matrix is not a unique, because I have already told you here for a given graph there will be so many number of number of trees. So because of that reason we can say there may be so many number of Dissect matrix also. So therefore it is not a unique matrix, and the total number of possible Dissect matrix is equal to, as the number of possible graphs is equal to the number of Dissect matrices. So therefore we can say the number of possible Dissect matrices is equal to the number of trees for a given graph. So therefore n to the power of n minus 2, and the rank of Dissect matrix is equal to n, because here the order of, or we can say the number of rows of this Dissect matrix is equal to the number of links. So because of that manner only we are going to say it is the number of the rank of a Dissect matrix is equal to the number of rows which are present in the Dissect matrix is equal to L. L is called as the number of links. It is also called as the complementary chords, complementary trees, or chords or links. These are the different names for the Dissect matrix, or we can say the different names of the links. Cascade matrix is not unique, because Cascade is also we are going to do with the help of the tree diagram. So therefore as the trees are not unique, so therefore Cascade matrix is also not a unique matrix. But the total number of possible Cascade matrix is equal to, same thing here, the total number of Cascade matrix is equal to total number of trees for a given graph, which is equal to n to the power of n minus 2, and the rank of Cascade matrix is equal to n minus 1, because here the rank is equal to the number of rows present in the Cascade matrix is equal to the number of peaks, which is n minus 1, whereas the rank of the Dissect matrix is equal to the number of links is L, whereas the rank of the Cascade matrix is equal to number of rows is equal to number of peaks, which is n minus 1. And I have already told you the relation, which is the number of links is equal to total number of branches minus of number of peaks, which is L is equal to B minus of n minus 1. So the total number of tree branches is equal to total number of nodes minus 1. The total number of tree branches, so the total number of tree branches is equal to capital N minus 1, which is total number of nodes minus 1. And the rank of incidence matrix, because the rank of the incidence matrix means, we can say clearly the rank of incidence matrix means the total number of rows. The total number of rows are n minus 1, so therefore this is called as the rank of reduced incidence matrix is equal to n minus 1. Whereas rank of a graph is equal to the number of peaks is equal to n minus 1, whereas the rank of trees also is equal to n minus 1. This is number of trees components. So then the rank of tree means the number of components, the number of branches present in this tree is equal to n minus 1. So I have already told you the total number of basic loops is equal to total number of links, which is equal to b minus of n minus 1. So these are some of the important formulas in the graph theory. Now I am going to tell you some of the important simple concepts. Suppose there is a primary winding and secondary winding. Primary winding is going to have self-inductance of L1, whereas the secondary winding is going to have a self-inductance of L2. And the number of turns in the primary winding is N1, and the number of turns in the secondary winding is N2, where M is the mutual inductance between the L1 and L2. So therefore here I already told you the relation, which is coefficient of coupling is equal to M by under root over L into L1, where K is going to lie between 0 to 1. So therefore M is going to lie between 0 to under root over L1 L2. So therefore M is equal to K into under root over L1 L2, where the inductance of any coil is directly proportional to square of the number of turns by reluctance of this coil. So therefore L is directly proportional to N1 square. So therefore L1 is directly proportional to N1 square and L2 is directly proportional to N2 square. Do the division of L1 by L2, we are going to get N1 by N2 whole square. So if you apply the square root on the both sides, we are going to get N1 by N2 is equal to under root over L1 by L2. So therefore you can see clearly the turns ratio is equal to square root of their inductance. So therefore the turns ratio is equal to the 1 by N2 is equal to under root over L1 by L2. You can see clearly this is independent of the mutual inductance. This ratio is independent of the mutual inductance. So now suppose there is a two vectors of voltage of Vrms and the current of Irms, and theta is the angle between these two vectors. Then the average power is equal to Vrms into Irms into cos of angle between these two graphs or between these two vectors, which is cos of theta. So when theta is equal to 180, we are going to get cos 180 is nothing but -1. So we are going to get P average is equal to minus Vrms Irms. So this is the value we are going to get, average power of minus Vrms Irms. Of negative value we are going to get. So now some more simple concepts we are going to learn here. See, I have already told you there is an inductor. This inductor current is I of t and the voltage across the inductor is VL of t. Then I am going to assume initial current through this inductor is I of 0. Then I can replace this circuit into this fashion I have already told you, which is here in the format of Laplace domain. This is going to become SL. In parallel there will be a current source of I0. But here I0 by S. So if you are going to convert it in the practical voltage source, we are going to get SL into I0 by S, we are going to get L into I0. So this is the polarity you are going to get, minus plus. So therefore we can say this is I of S and this is VL of S. So here, in case if you forgot this one, you can use even this formula, which is VL of t is equal to L into di by dt. So if you apply the Laplace transform, we are going to get VL of S is equal to L into S into S I of S minus I of 0 minus. So if you do the multiplication, we are going to get VL of S is equal to SL I of S minus L I naught 0. So therefore, if you apply the KVL in this loop, we are going to get minus 2 plus is plus 2 minus is minus, again minus 2 plus is positive. So if you rearrange this one, we are going to get VL of S is equal to SL into I of S minus L I naught. So this is the, even if you know this one also, you can blindly get this graph. So some more simple concepts now we are going to learn. Suppose here, this is a circuit. Here you can see clearly here, this is the voltage source, but here there is a load of RL plus JXL, but there is a RS and JXS, internal impedance. So now for maximum power transfer to load, the condition is I have already told you, which is this should be always, means the circuit should be always purely resistive, then only it can be possible. So therefore XS plus XL is equal to 0, so therefore XS is equal to minus XL, then only we can say the circuit is purely resistive, then we can get huge amount of power from the source to the load, means the maximum power is going to absorb by source to the load. Some more simple concept now we are going to see here. Suppose there are two voltage sources, two practical voltage sources are connected in parallel, and then I am going to connect another resistor of R3. Then the current through this R3 is, let me assume I of t. Then if V1 of t is equal to Vm1 sin omega 1t and V2 of t is equal to Vm2 cos omega 2t. So you can see clearly these two voltage sources of different frequencies. As omega 1 is not equal to omega 2, then I of t can be easily figured out by the Biliman's theorem. So we can figure out the value of the current I of t only with the help of the Biliman's theorem. So, or we can apply even the superposition theorem also, you can apply to get the value of the I of t. So therefore, but you can easily figure out with the help of the Biliman's theorem. Suppose there is a circuit like this, L1, L2, L3 are connected in series, and you can see clearly here, this the dot indicates the current is going to enter, and here so this is the dotted here. So now here M1 is the mutual inductance between the L1 and L2, whereas M2 is the mutual inductance between the coil 2 and coil 3, where M3 is the mutual inductance between the coil 1 and coil 3. So now I want to know what is the equivalent inductance. So to write this equation first, because these three are connected in series, so therefore L equivalent is equal to L1 plus L2 plus L3. But you can see clearly here the current in this direction. Then suppose if current in this direction, you can see clearly here current is entering the dot, and here also the current is going to enter the dot. So therefore coil 1 and coil 2, in both the things the current is going to enter the dot simultaneously. So therefore we can say these are in additive polarity and also series. So therefore plus 2M1. Whereas you can see now L1 and L3, you can see clearly here the current is going to enter the L1, but it is going to leave the L3. So therefore they are opposite or we can say they are opposite in nature, means that there is a opposition. So therefore we can say we have to go for the minus 2m3, but here L2 and L3, here the current is going to enter the dot, but it is going to leave the dot. Again there is a series opposition, so therefore again minus 2m3. So this is called as a equivalent inductance, which is L1 plus L2 plus L3 plus 2m1 minus 2m2 minus 2m3. Whenever there is a series aiding, we say it is a plus, otherwise series opposition means go for the minus. So now some more important points now we are going to learn in the electric circuits, which is an element is said to be linear whose VI characteristics follows only one equation of straight line passing through origin for all time, otherwise said to be non-linear element. Means an element is said to be only linear when the VI characteristic graph is going to pass through origin for all the time, then only we can say it is said to be a linear element, otherwise it is a non-linear element. In the plot VI, if the graph lies in first or only in third coordinate or in both, then the element is said to be passive. See here, if the graph of VI of any element is going to lie either in only 1 or in 3 or in both 1 and 3, we can say always the product of the voltage and current is always positive. So therefore it is always going to accept the energy, or it is always going to accept, or we can say to dissipate energy. So because of that we are going to say it is a passive element. In the plot VI, if the graph lies in second or only in fourth or in both, then the element is said to be an active element. So therefore we can say if the plot of VI is going to lie either in the second or in fourth or in both, then the product of the voltage and current is always negative. So therefore we can say that the element is said to be always an active element. An element is said to be bilateral only when it offers same impedance when the direction or the polarity of voltage or current get reversed, otherwise unilateral. See, an element is said to be bilateral only when, suppose you are going to reverse the voltage, then the impedance of the circuit should be same, remain same even if you are going to change the polarity of the voltage or polarity of the current. If it is not same, indicates that it is not a bilateral element, or simply we can say it is a unilateral element. Otherwise we can say it is a bilateral element. So therefore, even if you are changing the polarity of the voltage or current, if the impedance is going to remain same, then we are going to say that that element is said to be a bilateral element, otherwise it is said to be a unilateral element. Every linear element is a bilateral, but converse is not true, because always every linear element will be always a bilateral, but the converse is not true, because we can see clearly here for every linear element the bilateral is going to always satisfy, but a bilateral element may not even satisfy the linearity property. So that is the reason we can say, because bilateral there may not be condition of a straight line, it can have so many graphs. So because of that reason only we can say always if a element is linear means it is definitely bilateral, but if an element is bilateral means we can't confirm that is a linear element. That is a very important point here. An element is said to be time variant when its VI characteristics changes with time, otherwise we are going to call it as a time invariant element. Means if the time is going to changes, if the characteristics of VI is going to change with respect to time, then we say it is a time variant element, otherwise it is a time invariant element. An active element can behave as passive element under a given circuit, but a passive element will always behave as a passive under any circuit condition. See, it's a very important point here. An active element can behave like a passive element under a given circuit condition, but a passive element will be always passive no matter whatever the circuit you are going to put here. Because if you take an example of a mobile charger, here the battery, suppose if you are going to off the mobile charger, then we can say the battery is going to dissipate the energy, so it is going to act like a source. But if you want the charging of a battery, you are going to plug in the plug, so therefore now the battery is going to get charged, so it is going to act like a passive element. So therefore we can say an active element can behave like a passive under a given circuit condition, but a passive element will be always passive no matter whatever the circuit condition you are going to keep it. Now we are going to learn some important points regarding the KCL. Sum of incoming currents is equal to sum of outgoing currents. See, at any node or junction, always the sum of incoming currents is equal to sum of outgoing currents. It is applicable to only lumped circuit but not distributed network. So this KCL is going to apply only for the lumped circuits. Lumped circuits means you can represent it mathematically by a given figure, that we are going to call it the lumped circuit, but not for the distributed network. So therefore KCL and KVL are applicable only for the lumped circuit but not for the distributed network. It is applicable for any nature of element and it follows the law of conservation of charge. So therefore here For lumped circuit means you can apply anywhere KCL, but here it is going to be based on the law of conservation of charge. According to Diligence Theorem, the algebraic sum of power at any instant is equal to 0, or simply we can say that at any instant whatever the power delivered is equal to power absorbed. So if you take any circuit, the power should be always equal. It should be balanced, means some elements are going to deliver the power and the remaining elements are going to absorb the power. So therefore this should be always equal. Or simply if you go for mathematical notation, then we can say the algebraic sum of power at any instant in the given circuit should be always equal to 0. So if you take this element, you can see clearly this is a plus minus and the current is going to enter the positive terminal of voltage. We can say this element is going to absorb the power. See, if this is the case, means if the current is going to enter the positive terminal of the voltage, then we say this element is going to absorb the power. So this element is absorbing the power. But if the current is going to leave the positive terminal of the voltage, then we are going to say that this element is going to deliver the power. Means it is going to act like a active source. So this element is going to deliver the power. Ideal current sources connected in series only if they are of same magnitude and direction. See, whenever you want to connect two current sources, two ideal current sources, then definitely their magnitude value should be equal and also their direction should be equal. Then only the KCL is going to get satisfied. Otherwise, the KCL is not going to get satisfied. That is the reason whenever you want to connect two ideal current sources, their magnitude values in series, then definitely their magnitude value should be equal and also their directions also should be equal. Two ideal voltage sources connected in parallel only if. See, you can connect two ideal voltage sources in parallel only if their magnitude values are equal and also their polarity is also equal. Then only we can say we can connect like that. Otherwise, their KVL is going to get unsatisfied. That is the reason two ideal voltage sources, whenever you are going to connect in parallel, their magnitude values are equal and their polarities are also equal. They are of equal in magnitude and also same polarity. Internal resistance of an ideal ammeter is 0. Basically, internal resistance of ideal ammeter is 0 and internal resistance of ideal voltmeter is infinity and internal resistance of ideal current source is infinity and internal resistance of ideal voltage source is 0. It's a very important point here. Internal resistance of ideal ammeter is 0 and internal resistance of ideal voltmeter is infinity and internal resistance of ideal current source is infinity and the internal resistance of the ideal voltage source is 0. Suppose there is an LTI system, if the input is x of t and the output is y of t. So basically the output is going to have both the components which are the transient response and also steady state response. If the system is stable, then the transients die out and we get only steady state response. Suppose what is going to happen is here, basically the output is going to contain both the transient response and the steady state response. If the system is stable, means all the poles of the LTI system are going to lie in the LHS of S plane, then the transient is going to get die out, only the output is going to remain only steady state response. So therefore we can say if the system is stable, the transients will die out and we get only steady state response. So in a capacitor, the voltage across the capacitor is Vc of t and this is the current I of t. Then the expression of this one is I of t is equal to C into du by dt. So if you do the reverse process, we are going to get Vc of t is equal to 1 by C integration of minus infinity to t I of t dt. Whereas here in an inductor, the voltage across the inductor is VL of t and the current through the inductor is I of t. So therefore, the relation between them is VL of t is equal to L into I of t by dt. So if you do the reverse process, we are going to get I of t is equal to 1 by L integration of minus infinity to t VL of t dt. So therefore, you can see clearly the I of t is going to depend on the past values of current and also your Vc of t is going to depend upon the past values of the current. So therefore, we can say clearly that voltage is called as a state variable for a capacitor and current is called as a state variable for a inductor. So therefore, current cannot change instantaneously for this one inductor and the voltage cannot change instantaneously for a capacitor. If I am able to separate the elements, then only I am eligible to use these two crazy formulas. See here, suppose if I am able to separate the elements of resistance and capacitance or resistance and inductors, then I am going to eligible to use these formulas, otherwise we don't have to. So therefore here, if you want the capacitor voltage at any time which is equal to FIF, the basic formula is, you have to remember, this is final value, initial value, final value, here plus sign and here minus sign, into e to the power of minus t by 2, t is going to lie between 0 to infinity. Similarly, if you want the value of current of inductor, final value, initial value, final value, here plus and here minus, here into e to the power of minus t by 2. So therefore, t is going to lie between 0 to infinity. So these are the formulas that we need to do. So these formulas you can apply for these state variables. So voltage across the capacitor and the current in an inductor. So therefore, so F by F. So final value, initial value, final value, a positive or negative into e to the power of minus t by tau. A network is said to be symmetrical if we divide the network into two parts, then one should be mirror image of the other. Or if network looks same from both input and output ports, then it is said to be a symmetrical network. Suppose there is some network. So if you are going to see the network from this side, whatever the elements are you are going to get, and if you see from here also same amount of elements if you can see, then we say that no matter whether you are seeing from input or output, the circuit is going to look same. Then we say that the circuit is said to be a symmetrical circuit. So therefore, a network is said to be symmetrical if you divide the network into two equal parts, and then one should be the mirror image of the other, or the network looks same from both the input and output ports. Then we say it is a symmetrical network. A network which obeys reciprocity theorem, all passive networks are reciprocal networks. So very important point here. See, all passive networks are definitely reciprocal networks. See, if a circuit contains all the passive elements, it indicates that that network is said to be a reciprocal network. Now we are going to discuss about the here. I have already told you the relation between the Y matrix and Z matrix, which is Y matrix is equal to inverse of Z matrix, or we can also say that Z matrix is the inverse of the Y matrix. Similarly, T dash matrix is the inverse of the T matrix. Similarly, T matrix is equal to inverse of the T dash matrix. Whereas G matrix is equal to inverse of the H matrix, or the H matrix is equal to inverse of the G matrix. So now I am going to discuss some of the important relations of the sine and cos, which is sine of 90 plus phi. See, whenever there is a 90 means the sine is going to change to cos. 90 plus phi means it is a second coordinate. In the second coordinate only sine and cosec are positive. So therefore we can say now as there is a sine here, so we have to keep here plus symbol. Sine of 90 minus phi. So whenever there is a 90, phi changes to cos. And also 90 minus 5 is first coordinate. In the first coordinate each and everything is a positive, so therefore sine is going to change to means each and everything is positive, so therefore you have to keep your plus sign. Cos of 90 plus 5. So whenever there is a 90, cos changes to sine, and 90 plus 5 is second coordinate. In the second coordinate only sine and cosec are positive, so therefore cos is negative, so therefore that is the reason you have to keep a minus symbol. Cos of 90 minus 5. So here whenever there is a 90, cos changes to sine, and 90 minus 5 is first coordinate, so each and everything is positive, so cos is also positive, so therefore you have to keep a plus symbol. Similarly, cos of 5 minus 90. So 5 minus 90 you can also write, which is minus of 90 minus 5. But there is one property of cos, which is cos of minus theta is equal to cos theta, because the cos function is symmetrical with respect to y-axis. So because of this reason only we can say that cos of 5 minus 90 is equal to cos of 90 minus 5, that we have already discussed, which is equal to sin phi. Here cos phi you can write either sin of 90 plus phi or sin of 90 minus phi. Similarly, sin phi you can write either cos of 90 minus phi or cos of 5 minus 90. You can go for any of the things. Whereas minus sin phi you can write, which is cos of 90 plus phi. So this is very much important if you want to convert cos to sin and sin to cos. When both sine and cosine excitation having same frequency is given, see, if nothing is specified, then those are the RMS values by default, or when nothing is given about excitation, then always take that value as the RMS value. Suppose in the excitation they are not going to give you whether it is a maximum value or the RMS value, then definitely we have to include it, or we can by default we have to use them as the RMS value. So if nothing is specified, then those are the RMS values by default, or when nothing is given about excitation, then always take that value as the RMS value. So in the question sometimes they are going to give you the excitation as some values, but they are not going to mention whether these are the maximum value or the RMS value or the instantaneous value. Then default this indicates that these are the RMS values. Only sinusoidal excitation is given, then take sine as the reference. So here suppose if each and every source are in a term of sine function, then you have to take sine as the reference. When only sinusoidal excitation is given, then take cos as reference. Means if each and every source in the terms of the cos, then we can take cos as the reference. When both sine and cosine excitation having same frequency is given, then take any one as a reference and make others on the same reference. So here suppose in a circuit there are some excitations of the sine and some more of the cos. and both are, and each and everything is going to have the same frequency, then default we can choose any one as the reference and we can solve the question. Means it indicates that suppose in a complex circuit, see there are some sources of sine in nature and some are cosine in nature, but each and every source is going to have a same frequency. Then how we are going to solve this numerical is convert all the sines into cos. So therefore each and everything is in the terms of cos, and take the cos as a reference, and then you can solve the question. Or way that convert all the cos into sine and each and everything in the terms of frequency of same frequency with the sine, then you can solve this question and you can get the numerical value of the response. So in the both methods you are going to get the same result. When both sine and cosine excitation having different frequency is given, then only superposition method can be applied to solve. When both sine and cosine excitation having different frequency is given, then only superposition method can be applied to solve. Suppose in a given circuit there are sine sources and also cosine sources but of different frequency, then the only way to solve this numerical of to find any response is by using the superposition method. The superposition method is finding the response in any branch by taking only one source at a time. So therefore, if you want to know what is the response due to so many sources acting simultaneously, it is equal to the response, or we can say the algebraic sum of the response at each and every source acting alone. Then that is called a superposition. So these type of questions of different frequency sources, it can be solved only by the superposition. When the phase difference between the supply voltage and the supply current is zero in any combination of RLC circuit, then it is called as a resonance. When the phase difference between the supply voltage and the supply current is zero in any combination of RLC circuit, then it is called as a resonance. So basically resonance means here simply if you take any RLC circuit, means definitely for a resonance there must be two energy storing elements. One should be either of magnetic nature and the other should be of electric nature. So then what is going to happen is at resonance the voltage applied and the current to the source both should be in phase. Means we can say simply the circuit is purely resistive. Then only we can say there is no phase difference between the supply voltage and the supply current at the resonance. So now selectivity is inversely proportional to bandwidth and it is directly proportional to quality factor. I have already told you that selectivity is also called as the quality factor and it is inversely proportional to the bandwidth. This is a very important relation. So quality factor is always inversely proportional to the bandwidth. So if the bandwidth is very high, then quality factor is very less. But if the bandwidth is very less, then the quality factor is very high. At resonance circuit, circuit is purely resistive and impedance and admittance also. So therefore, if at resonance condition, if you take any complex circuit, it will be always resistive. It means the impedance and the admittance is going to have only the real part but not the imaginary part. But that is the beautiness of the resonance. So current enters from dot or leave the dot simultaneously, then the mutual flux aids the main flux and the voltage induced by mutual flux is positive. So what is going to happen is basically here, if suppose the currents are going to enter the dotted of the two coils simultaneously or leaving the dotted simultaneously from both the coils, then we can say both the fluxes will be in the same direction. So because of that the voltage is going to get increased, or the mutual flux will in the same direction as the original flux. So therefore the voltage induced is going to get increased. So we have to go for the positive sign. Current enters from dot in one coil and leave the dot in the other coil, then the mutual flux opposes the main flux and the voltage induced by the mutual flux is negative. So what is going to happen is basically here if you take two coils, one current is going to enter the dot and the other current is going to leave the dot. So because of this nature, the mutual flux and the original flux are going to opposite in nature. So therefore the voltage is going to get decreased. So therefore the voltage induced due to mutual flux should be always negative. So CA2 and the bilaterality property is satisfied by a non-linear circuit. So always see a non-linear circuit will never satisfy. A non-linear circuit will never satisfy a superposition principle, but it can satisfy the associative property and also the bilaterality property. An iron core inductance coil can be modeled over a normal operating range of networks as a linear bilateral element. See, suppose there is an iron core, on that you are going to turn some of the coils or you are going to own some amount of coil, then we can say we can model for a normal range of frequencies, we can model this as a linear bilateral element. Statements with respect to a high Q series RLC circuit under resonances. So if you take a series RLC circuit with a huge amount of Q factor, then some of the important points now we are going to study at resonance. The voltage across the resistor is equal to the applied voltage. Yes, at resonance definitely whatever the supply voltage is equal to the voltage across the resistor. The voltages across L and C are equal in magnitude. Yes, they are both are equal in magnitude, but the phase difference of 180 is going to get present between them. And the voltages across L and C are maximum at resonance also. A resistive network is always reciprocal. See, reciprocal means the ratio of the excitation to the response is always going to remain constant, no matter if you are going to interchange the response to excitation and the excitation to response. That is the meaning of the reciprocal. So therefore, if you take a linear network, if you take a resistive network, the resistor is nothing but it's a linear element and the bilateral. So everything is satisfied. So therefore, we can say the reciprocal property is going to get satisfied for the purely resistive network. See, now we are going to study the relation between the inductance and the number of turns of the coil. So L is directly proportional to square of the turns of the coil. So it is equal to, we can say, this is the way the inductance and the turns of the coil are going to get related. So L is directly proportional to N square. As the number of turns of coil increases, the inductance increases with this relation, which is L is directly proportional to N square. Whereas R is directly proportional to N. N is called as the number of turns of, whereas R is called as the number of turns of the coil, and R is the resistance of the coil. As the number of turns of the coil are going to increase, this is the way in which the resistance of the coil is going to get increased. So therefore, as number of turns of coil increases, the resistance increases with this relation. The instantaneous power in the three-phase system is constant at any time, and it is equal to the 3 times the average power. This feature is of great value in the operation of three-phase motors, where the constant instantaneous power implies an absence of torque pulsation and the consequent vibration. See here, the instantaneous power in a three-phase system is always constant in nature. So because of this, we can say that there will be a absent of the pulsation, torque, and also vibrations are going to get absent. So, but in a single phase, what is going to happen is basically the instantaneous power is alternating. It is going to change with respect to time. So the torque is going to get changed. So therefore, there will be a lot of vibrations. But if you take in terms of three-phase supply, then definitely the instantaneous power is a constant value. So because of that, the torque vibration is 0 and there will be no vibrations. If the pole is nearer to the origin in LHS, then f of s is an RC impedance function. Suppose if you take an RC circuit, series RC circuit, and if you try to figure out the impedance of this RC network, and if you try to figure out the pole zero plot of this impedance function in the S plane, then definitely you are going to get one pole which is nearer to the origin in the LHS plane. That is the meaning of the RC impedance function. So now we are going to discuss here, there are two bulbs. So the bulb 1 is going to have a power rating of P1 with a voltage rating of V1. Then the bulb 2 is going to have a power rating of P2 with the same voltage rating of V1. And if you are going to connect a voltage source of V1, same, all the bulbs, 2 bulbs has the same voltage rating and the same voltage now we are going to apply across this series connection of bulbs. Then what is the total amount of power absorbed by these 2 bulbs is equal to P1 into P2 by P1 plus P2. So this is the only formula when they both have the same voltage, and that same voltage we are going to apply. Otherwise, this is not going to be true. So therefore, this formula you should apply only when they both have the same voltage rating and the same voltage is applied across them, which is P absolute is equal to P1 P2 by P1 plus P2. Where P absolute is equal to the total power given by voltage source V1, means whatever the power which is given by V1 is equal to the power absorbed by these 2 bulbs. By compensation theorem or substitution theorem, the impedance Z of branch with current I flowing through it can be increased from Z to Z plus Z small amount of Z. The solution of the network will remain the same if an EMF of minus I into delta Z is introduced in series with the branch. So I have already told you the compensation theorem or the substitution theorem, whether you can replace the resistor by either voltage source or current source, but the voltage and the current of the remaining circuit should not be changed. That is the thing that we need to take care. So if this impedance is increased by Z plus delta Z, then we have to substitute another parameter of a small amount of EMF of minus I into delta Z blue. So therefore overall will remain same as the previous one, then we are going to get the same result of the remaining circuit also. So therefore, by completion theorem or substitution theorem, the impedance Z of a branch with current I flowing through it has increased from Z to Z plus small amount of Z. The solution of the network will remain the same if an EMF of minus I delta Z is introduced in series with the branch. So Z was increased from Z to Z plus small amount of Z, delta Z. So therefore now we have to keep a EMF of voltage minus I into delta Z. So therefore overall circuit voltage will remain same. So therefore we can say each and every parameter of the remaining circuit is unchanged. In a series RLC circuit, suppose if you take a series RLC circuit, here if you are going to draw the voltage across the capacitor and the voltage across the inductor with respect to the frequency, you are going to get in this relation. For a series RLC circuit, I have already told you, for a frequency greater than F0, the circuit will be lagging in nature, whereas a frequency less than F0, for a frequency less than F0, we know that the circuit is leading in nature, but for a frequency greater than F0, the circuit is in lagging in nature. So because of that, here it is a leading. So therefore, capacitor will reach maximum value of the lower cutoff frequency, whereas at higher cutoff frequency, the voltage VL, the voltage across the inductor is going to reach the maximum. But at resonant frequency, both the magnitude of the capacitor voltage and the magnitude of this inductor voltage are same. For F1 we are going to call it as the lower cutoff frequency, and F2 we are going to call it as the upper cutoff frequency. And I have already told you the relation between the quality factor and the bandwidth, which is quality factor is equal to resonant frequency by the bandwidth. Bandwidth is directly proportional to frequency when Q is constant, whereas the bandwidth is inversely proportional to quality factor when F0 is constant. See, when F0 is constant, they are inversely related, but when Q is a constant, then bandwidth is directly proportional to F0. As the order of low pass filter increases the slope, the frequency response of filter will be increased. So fast drop in filter response. See, whenever you are going to increase the slope, or we can say order, then we can say that the graph is going to decay very faster. So you are going to get an ideal filter. So therefore, as the order of low pass filter increases, the slope, the frequency response of the filter will be increased. So that fast drop in filter response means if you are going to increase more and more, it is going to become nearly an ideal low pass filter. Diligence theorem applicable to linear, nonlinear, active and passive elements. Yes, no matter whatever the elements which are going to present in a circuit, always the diligence theorem is going to always hold. Means the power delivered by all the sources is equal to the power absorbed by the elements. So power will be always satisfied. So some more relations, which is cos of theta minus 180. So if you take minus common, we are going to get cos of minus of 180 minus theta is again equal to cos of theta minus 180. So therefore cos of minus theta is equal to cos theta. So because of that, they both are equal. So therefore we can say it is equal to, whenever there is a 180, cos is to cos. But 180 minus 5 is a second coordinate. In the second coordinate only sine and cosec are positive but not cos. So therefore you have to go for a minus symbol. So sine of theta is equal to, you can write cos of 90 minus theta is equal to cos of theta minus 90. I have already told you this relation just now only. Network is a combination of elements which may or may not consist of closed parts. See, network means it is going to just connect elements. It may or may not have closed parts. Whereas circuit is a combination of elements and it should contain and it should consist of closed parts. See, if there is a closed parts means it definitely is a circuit. Otherwise, it may or may not, then it indicates it is a network. So simply we can say that all circuits are networks, but all networks are not circuits. Outside the circuit, electron goes from negative terminal of the battery to the positive terminal of the battery. So therefore you can see clearly outside the battery, the electron goes from negative terminal of the battery to the positive terminal of the battery. But inside the battery, the electron goes from positive terminal of the battery to the negative terminal of the battery. The relation between the current and the charge is I is equal to dq by dt. So if you take the integration on both sides, we are going to get charge is equal to integration of minus infinity to t I into dt, where the unit of the charge is coulomb, whereas the unit of the time is second, whereas the unit of the current is ampere. The force on the electrons is carried by EMF. EMF means electromagnetic force. So because of this voltage only, the force is going to get created on the electrons, so they can move from one place to the other place within a conductor. The voltage means the rate of change of work, means the amount of work done per unit charge. The amount of work done to bring a unit charge from infinity to any particular point is called as the voltage. So V is equal to dW by dQ. So we can also write, suppose P is equal to the rate of change of work, which is P is equal to dW by dt. So you can write dW by dt into two fashions, which is dW by dq into dq by dt. So dq cancels, we are going to get final dW by dt. So dW by dq is nothing but voltage and dq by dt is current. So therefore power is equal to voltage into current. So P is equal to VI, but I have already told you in the Ohm's law, V is equal to IR. So if you replace V is equal to IR, we are going to get I square R. But here you can replace I is equal to V by R, you are going to get V square by R. But 1 by R is nothing but conductance. So therefore V square into G. So you can apply any of this formula. But R is equal to 1 by G. So V is called as the voltage and P is called as the power. Q means charge, W means work, and I means current, R means resistance, and G means conductance. These are the symbols meanings. So you can see clearly there is an element here. The current is going to enter the positive terminal of the voltage, means this element is going to absorb the power. Whereas here this element, the current is leaving the positive terminal. So therefore we can say this element is delivering the power. The capacity to do work is called as the energy. So the capacity to do work is called as the energy. This is the definition of the energy. So energy is equal to integration of 0 to 2 T P of T into dt. So energy is equal to integration from 0 to T P of T into dt. Whereas the units of the energy is, the unit of power is watt and the unit of time is second. So therefore if you multiply these two things, we are going to get a joule. So joule is equal to watt into second. When the element is capable of delivering energy independently for a long time, approximately infinity, or when the element is having internal amplification, then it is called as an active element. So basically the meaning of active element means here this element can deliver the energy for very long amount of time, approximately infinity, or if this element is going to have some internal amplification, then only we can say that elements are the active element. So therefore active elements means whether they can have internal amplification or whether they can deliver the energy for a lot amount of time. That is the meaning of the active element. So the active elements are example voltage source and current source. These are called as the independent sources. Whereas a transistor and op amp, because the voltage across one element is going to depend upon some other parameter in that circuit, so we are going to call this as the dependent sources. But each and everything is an active, but the only thing is their sources is going to depend upon some other parameter, so because of that only we are going to call it as the dependent sources. Capacitor can deliver energy only up to 5 tau, so it is not an active device, because capacitor can deliver the energy only up to 5 term constant. So it's called as a passive element. During discharging, capacitor can deliver energy independently for short time, and capacitor is not having property of internal amplification. See, a capacitor can deliver only up to energy up to a certain amount of time, and it doesn't have even any internal amplification. So because of this reason we say capacitor is not an active element, or simply we can also call it as the capacitor is a passive element. When the element is not capable of delivering energy independently, then it is called as a passive element. Suppose if any element it can't deliver any energy independently from, it is not depending upon any other, then we can say it is a passive element, means it can absorb the energy. Some of the examples are resistor, bulb, transformer. These are the passive elements because these are going to absorb the power. They are going to dissipate some amount of power. Ideal voltage source delivers energy at specified voltage, which is independent of current delivered by the source, and internal resistance of the ideal voltage source is equal to 0. Since VI characteristics is nonlinear, so it does not satisfy Ohm's law. I have already told you, for ideal voltage source, the voltage value is always constant no matter whatever the current is going to flow through that ideal voltage source. So, and it doesn't even follow the Ohm's law because there is nothing like a straight line passing through origin. It is a horizontal line. So therefore we can say it is not going to even satisfy the Ohm's law. Practical voltage source delivers energy at specified voltage which depends on current delivered by the source. For a practical voltage source, there will be a small amount of internal resistance, but the internal resistance is absent for the ideal voltage source, but it is not 0 for the practical voltage source. So because of that, whenever the current is going to get changed, the load voltage is also going to get changed. So whenever the current increases, the load voltage is going to get decrease. If any circuit not obeying KVL or KCL, then the circuit won't exist in this world. Yes, if you take any circuit, if in that circuit if the KVL or KCL is not obeyed, means that circuit is physically we can't make that circuit physically. If any circuit not satisfying Kirchhoff's laws, then you don't have to use superposition theorem to figure out the particular response. See, if any circuit not satisfying the KVL or KCL, then it indicates that we can't build that circuit physically. So therefore, you don't have to go for any other theorems. You don't have to apply any theorems to solve the question. So therefore, always if a circuit you can physically build it, then only you go for the analysis part. Otherwise, you don't have to go for the analysis part. Ideal current source delivers energy at specified current Is. See, always the ideal current source is going to have a constant current Is, which is independent of the voltage across the source. So no matter whatever the source voltage, it will be always equal to Is, and it has infinite amount of internal resistance. Internal resistance of ideal current source is infinity. Just now I told you, for ideal current source, the internal resistance is infinity. For ideal voltmeter, internal resistance is infinity, and for ideal current ammeter, the internal resistance is 0. These are the basic points. Practical current source delivers energy at specified current I, which depends on the voltage across the source. So therefore, we can say clearly that for a practical current source, there will be a high amount of resistance across it. Internal resistance is not 0. So we can say that now the current absorbed by the load is going to depend upon the voltage. That is the meaning of the practical current source. Independent current source does not satisfy the Ohm's law since VI characteristics is nonlinear. Same as the ideal voltage source, because here also we are going to get a straight line. So therefore, but it is not passing through origin. So because of that reason only, it is not going to satisfy even the Ohm's law. In the practical system, no independent current source is exist, but dependent current source is exist. Example, transistor. See, in the practical world, there is nothing like independent current source. Only we can get a dependent current source. The example is transistor, because IC is equal to beta into IB. So we can say that clearly it is a current controlled current source. There is only a dependent current source, but nothing like ideal current source. Suppose there are two resistors are connected in series. Then suppose we are going to apply a supply voltage source of V, then the voltage drop across the C1 is V1 and the voltage drop across the C2 is V2. Then I already told you that these two are in series, means the net capacitance is equal to C1 C2 by C1 plus C2. And if you want to know what is the V1, by applying the voltage division principle, V1 is equal to V into C2 by C1 plus C2, whereas V2 is equal to V into C1 by C1 plus C2. So if you do the division of V1 by V2, we are going to get C2 by C1, and if you do the cross multiplication, we are going to get C1 V1 is equal to C2 V2, because the charge is going to remain the same in a series circuit. So charge is equal to constant means C1 V1 is equal to C2 V2. So for resistor, the basic formula is V is equal to I into R. So but I is equal to dQ by dt. Or if you take here I is equal to V by R, so 1 by R is nothing but G. So these are the different relations of the resistor. For inductor, the expression of the voltage and current, which is V is equal to L di by dt. So if you take only current, means do the integration, we are going to get I is equal to 1 by L into integration of minus infinity to V into dt. But for capacitor, I is equal to C into dV by dt. So if you want V, which is 1 by C into integration of minus infinity to t, V of t into dt, I of t into dt. When element properties and characteristics independent on direction of current, then it is called as the bidirectional element, or bidirectional and bilateral both are same. See, bidirectional is also called as bilateral. It indicates that here, suppose if you are going to change the polarity of the either current or voltage, but still the impedance of the circuit is remain same, then we are going to say that element is said to be bidirectional or bilateral element. When element obeys the Ohm's law, then it is said to be linear resistor. See, if any resistor which is going to obey the Ohm's law, then we are going to call it as the linear resistor. Every linear element should obey the bidirectional property, but not vice versa. I have already told you, always every linear element is a bilateral element, but every bilateral element is not a linear element. See, this is a when bridge is at balanced. Suppose this is called as a Wheatstone bridge, and the bridge is going to balanced means the current in this ZY is 0. At that condition, you are going to get a certain condition, which is when bridge is at balanced condition, we get, suppose the current in this ZY is 0, then we are going to call it as the balanced bridge. Then the condition for that is the product of opposite impedance is same, which is Z1 into Z4 is equal to Z2 into Z3. So if the simplification, we are going to get Z1 into Z4 is equal to Z2 into Z3, or simply we can say Z1 by Z2 is equal to Z3 by Z4. At this condition, the current in the Z5 element is 0. So we can say as current itself is equal to 0 in the Z5 means we can easily neglect it or we can open it also. Resistance is the property of the resistor. It always opposes the current by doing so. So therefore, the property of the resistance is nothing but say property of the resistor means it is going to always be oppose the current. Whatever the current it is going to flow through any conductor, this is a property to oppose that one. This is we are going to call it as a resistance. It converts electric energy into heat energy. So because of this opposition, it is going to convert some electrical energy into heat energy. So resistance is nothing but a friction to flow of electrons. Yes, resistance means it is basically a friction to flow of electrons. So because of that, a small amount of energy is going to lost or dissipated. Suppose if you are going to take a conductor of length L and a cross-sectional area of A, and the current I is going to flow through this conductor. So therefore, the basic formula which is J is equal to sigma into E. This is called as the Ohm's law in the EMF. This we are going to call it as the Ohm's law in the EMF. So current density is equal to current per unit area, whereas conductivity is equal to reciprocal of the resistivity, where electric field is equal to voltage by distance, which is L. So if you substitute here and if you do the simplification, we are going to get V by I is equal to rho L by A. Rho L by A we are going to call it as a resistor. So therefore we are going to get V is equal to IR. This is the relation we are going to get from this one. When element properties and characteristics depends on the direction of the current, then it is called as the unidirectional element. See, if you are going to change the polarity of the voltage or current, if the impedance of the circuit is going to vary, then we are going to call it as the unidirectional element. Suppose if R is greater than or equal to 0, L is greater than or equal to 0, C is greater than or equal to 0, if you are going to get in this manner, then we are going to say that element is always a passive element. If you are going to get negative value means it is basically an active element. If V by I ratio is positive in both the coordinates, then the element is said to be passive. See, if you are going to do division or either multiplication, then if you are going to get always positive, then we are going to say it is said to be a passive element. If V by I ratio is negative either in both coordinates or in one of the coordinates, then it is said to be an active element. Suppose if the ratio or the division, if the ratio or the multiplication of voltage into current, if it is a negative, then definitely we can say that that element is said to be an active element. But if it is a positive means it is basically a passive element. Above two statements are valid when the characteristic is passing through the origin. So whenever the line is going to pass through origin, we have to apply these principles. When element obeys the bidirectional property, characteristics should be identical in the opposite coordinates but not in the adjacent coordinates. See, here bidirectional property means that an element is going to obey the bidirectional property only when the graph is going to lie in the two opposite coordinates but not in the adjacent. Means if one is going to present in one means it remaining has to present in the third. If suppose one is going to present in the second means the remainder should be present in the fourth. Then only the voltage by current division will be always positive. Then only it will be same. The voltage by current ratio will be always same. Superposition theorem is applicable to a linear network in determining only the current response and the voltage response but not the power response. So we are going to use the superposition principle only to get the response of current or the voltage but not the power, because current and voltage are only linear but power is not a linear quantity. So because of that reason only this theorem is not useful to figure out the power in any element. The locus of the tip of the voltage phasor across R in a series RLC circuit is a circle. So if you try to figure out what is the locus of the voltage across the resistor in a series RLC circuit, then you are going to get a locus of circle. The locus of the tip of the voltage phasor across the R in a series RLC circuit is always a circle. In a graph, direction of a fundamental loop is the corresponding link direction. I have already told you, in a fundamental loop, the current direction is the loop direction is equal to the current direction in the link. If A is the incidence matrix, then B is the fundamental loop matrix. Then the relation between them, which is A into B transpose, is equal to 0. So this is the basic relation between the incidence matrix and also the fundamental loop matrix, which is A into B transpose is equal to 0, where A is called as the incidence matrix and B is called as the fundamental loop matrix. In a fundamental loop matrix, the submatrix corresponding to the T branch is not an identity matrix. It's a very important point here. In a fundamental loop matrix, the submatrix corresponding to T branch is not an identity matrix. What I told you, in the fundamental loop matrix, there may be possible of identity matrix or may not be possible of identity matrix. Suppose if you take a small example of matrix A, you can see clearly the rows indicates the number of nodes, whereas column indicates the number of branches. So you can see clearly here, if you do the addition of the column, 1 minus 1 is 0, but here also 0, here it is not 0. So therefore we can say this is called as the reduced incidence matrix, because always in the augmented incidence matrix, each column summation will be always going to give you 0. But here in this one it is not equal to 0, means it is a reduced incidence matrix, called as a reduced incidence matrix. So you can see clearly here there are total number of branches are 4. So one of them is reference node, that's why I have removed here. But basically there are 4 nodes total, and there are how many branches? 1, 2, 3, 4, 5, 6, 7. So 7 branches are going to present and parallel connected between node 2 and node 4. So basically there are both 4 nodes and there are 7 branches. So you can see clearly the branch 4 is connected across the 2 and 4 node. Similarly branch 7 is also connected across the 2 and 4, because here the column is not 0, so you have to go for the minus 1 here, and this is also column is not equal to 0, so you have to go for the plus 1. So the branch 4 is connected across the node 2 and node 4, and the branch 1 is also connected across the node 2 and node 4. So therefore we can say these two are the parallel branches connected across the node 2 and node 4. So branch 4 and the branch 7 are parallel connected between the nodes 2 and 4. When a circuit resonates at a particular frequency, at that frequency the imaginary part of the impedance and the admittance of the network will be 0. I have already told you, for resonant frequency, definitely the circuit is purely resistive, means the imaginary part of the impedance and the imaginary part of the admittance is 0. If y11, y12 is equal to y21, then we say reciprocal and passive network. See, whenever this property is satisfied, I have already told you in the Y matrix. In the Y matrix, if y12 is equal to y21, then we say it is a reciprocal. Reciprocal means by default the circuit is a very passive network. If y12 is not equal to y21, means it is a non-reciprocal. Non-reciprocal means it is by default not a passive element, means some active elements are going to present in that circuit. KVL is based on the law of conservation of energy. So KVL is going to be based on the law of conservation of energy, whereas KCL is going to be based on the law of conservation of charge. So Ohm's law can be applied for lumped, linear and distributed parameter. See, Ohm's law we can apply for the both linear and also for distributed, because I have already told you J is equal to sigma A, that we are going to apply for the distributed, but for the lumped we are going to use V is equal to IR. So KVL and KCL fails for distributed parameters, since in these distributed parameters electrically it is not possible to separate resistance, inductance and capacitance effect. So KVL and KCL we can't apply for distributed parameters because we can't physically isolate the resistance, the inductance and capacitance. But Ohm's law we can apply for both lumped as well as distributed networks. So KVL, KCL are applied only for lumped parameters, linear, non-linear, unidirectional, bilateral, time variant and time invariant elements. So no matter what are the property of elements, it is always going to apply for the lumped parameter networks. KVL and KCL fails for high frequency applications. For wireless communications we can't write KVL and KCL. So therefore I have already told you, for high frequencies we can't isolate the elements. So because of that we can't write the KVL and KCL for high frequency applications. But we can write Ohm's law for both high frequency and also for normal frequency. Field theory can be applied for low frequency and high frequency applications. In the field theory, accurate results are obtained and developing mathematical equations is very complex. So in the field theory, it is going to basically apply for both the low frequency and also high frequency. But in the field theory, whatever the results you are going to get, they are highly accurate, but the mathematical equations are very complex. Network theory is applied only for low frequency applications. So network theory is only applicable for the low frequency applications, but not for the high frequency applications. In the network theory, approximate results will obtain and developing mathematical equations is very simple, because in the network theory it is basically applied for only low frequencies, and also the mathematical equations are very simple and we are going to get very approximate results but not the accurate results. KVL and KCL fails for high frequency applications. This point I have already told you, that is KVL and KCL is applied only for low frequency applications but not for the high frequency applications, whereas Ohm's law can be applied for both high frequency and also the low frequency applications. The resistance of equal value transferred from delta to star decreases by 3 times. This you can easily figure out by the help of the star delta conversion. Similarly, when capacitance of equal value transferred from delta to star, capacitance value increased by 3 times. This also you can figure out with the help of the star delta transformation. While applying source transformation for dependent source, where dependent source magnitude depends without disturbing that element, transformation can be applied. See, suppose if you are going to apply the source transformation of dependent source, then the dependent source parameter is going to depend upon some variable, that by not changing that variable you can do the transformation. So therefore we can say, while applying source transformation for dependent source, where dependent source magnitude depends without disturbing that parameter, transformation can be applied. Mesh means having no inner loop. Every mesh is a loop but not converse. Means here loop means every mesh is a loop but every loop is not a mesh, because in a mesh there are no inner loops. So because of that reason only we can say every loop is a mesh but every mesh is not a loop. Planar networks means no crossovers even after redrawing. Suppose if you are going to redraw the circuit, even after redrawing, if you can't make any crossovers in the circuit, then we say it is a planar network. Otherwise, non-planar network means there are definitely crossovers. Mesh analysis is applied only for the planar networks. So therefore, mesh analysis is only applicable for the planar networks but not for the non-planar networks. See, E is equal to B minus of N minus 1. This I have already discussed, which is here B is called as the number of independent parts in the circuit or branches, where N is called as the number of principal nodes, whereas E is called as the number of mesh equations. So always the number of mesh equations is equal to number of links, which is equal to B minus of N minus 1, where B is the number of branches present in the circuit, where N is the total number of nodes present in the circuit. So always the number of EMF, the number of mesh equations is equal to the number of links. So when the current source branch is common for two meshes, it is possible to find solution by using the super mesh technique. So between two meshes, if there is a current source, means we can only find the solution by using the super mesh technique. Nodal analysis is applied for both planar and non-planar networks. Means mesh analysis is only applicable for the planar networks but not for the non-planar networks. But the nodal analysis is applicable for all the planar networks and also for the non-planar networks. The number of nodal equations is equal to total number of nodes minus 1, which is equal to E is equal to N minus 1, or we can simply say that the number of peaks is equal to the number of nodal equations, which is E is equal to total number of node equations, or we can also call it a KCL, whereas N is the total number of nodes present in that circuit. When ideal voltage sources is connected between two non-reference nodes, it is possible to find solution by using the super node technique. So whenever there is an ideal voltage source, it is going to present between two non-reference nodes, then we can obtain a solution by using only the super node technique. When the bulbs are connected in series, lower rating bulb will give the more brightness. It's a very important point. Whenever the two bulbs are connected in series, always the lower rating bulb will always give the high amount of brightness. When the two bulbs are connected in parallel, the higher rating bulb will give the more brightness. It is quite opposite to the previous one. So whenever the two bulbs are connected in series, always the lower rating bulb will give the higher brightness. But whenever the two bulbs are connected in parallel, always the higher rating bulb is going to give you the more amount of brightness. Above two statements are valid only when the voltage rating of the bulbs are equal and for any supply voltage. See, this is only applicable when both the bulbs are going to have the same voltage rating and the supply voltage can be of any value. So now we will know about the advantage of the sine wave. It is easy to handle mathematically differential integral of the sine function. So we can easily do the differentiation and also the integration of a sine function. It can be again rewritten in terms of sine function. So therefore we can say clearly the differentiation of and the integral of any sinusoidal function is again a sinusoidal in nature. Natural phenomena like motion of the simple pendulum, strings of musical instruments and ripples in the ocean exhibits sinusoidal characteristics. So you can see all the natural phenomena in the world which are like the motion of the simple pendulum, strings of musical instruments and the ripples in the ocean are also going to exhibit the same sinusoidal characteristics. Any periodic waveform can be expressed in terms of the sine function by using the Fourier analysis. So by using the Fourier analysis, we can write any periodic function in the terms of the sine function, and it is easy to generate in the laboratory. So these are some of the advantages of the sine function. So therefore we can say the differentiation, the integration of sinusoidal is again sinusoidal, and also we can say that by using the Fourier series, we can write in terms of the any periodic function in the terms of the sinusoidal, and also we can easily generate in the laboratory, and also some of the physical or some of the applications, real-time applications are also in the terms of the sinusoidal. Some of the natural phenomena are also going to occur in the terms of the sinusoidal in nature. So these are some of the advantages of the sine function. AC voltages like 230 volt, 11 kV, 33 kV, 66 kV, 132 kV, all these are effective value, or we also call as the RMS of signal. See, 230 volt, 11 kV, 33 kV, 66 kV, 132 kV. If you are going to know these values, then by default these are called as the RMS value of the signal, or we can also call as the effective value of the signal. See, RMS value is equal to under root over 1 by t into integration of 0 to t v of t whole square into dt. Similarly, for IRMS is equal to integration of 1 by t into integration of 0 to t I of t whole square into dt. RMS is dependent on the concept of the same heat transfer in both the DC and the AC circuits. So if you go for the DC application and AC application, if you are going to keep the sources for same amount of time for a given load, the amount of heat dissipated in the both are going to be equal. That is the meaning of the RMS value. Average is dependent on the concept of same charge transfer in both DC and AC. So therefore, same heat means RMS value, and same charge means for both DC and AC, then we are going to call it as the average. So RMS is different in the concept of same heat for both AC and DC application, whereas average means a same amount of charge is transferred for both AC and the DC application. When the network is having bidirectional elements with respect to homogeneity principle, if excitation is multiplied with constant k, then the response of each element is also multiplied with constant k. While applying homogeneity principle in the network, only one independent source is activated. Homogeneity principle applicable for only voltage or current. See, I have already told you this point here. See, if a network is having bilateral elements, see, the homogeneity principle indicates that if the excitation is increased by a small amount of k, then the response of each and every element is also going to increase by same amount of k. And this homogeneity is going to applicable only in that network. Only one source is going to get present, then only this principle is going to get applicable. So therefore, when the network element is having bidirectional elements, with respect to homogeneity principle, if excitation is multiplied with constant k, then the response of each element also multiplied with constant k. While applying homogeneity principle in the network, only one independent source is activated. Homogeneity principle applicable for only voltage and current. It is only applicable for the voltage and current, but not for the power. Suppose there is a circuit like this. The current, the first source is of I of t and the second is of I2 of t, and there is a resistor R. If suppose I1 of t is equal to I1 into sin omega 1t and I2 of t is equal to I2 into sin of omega 2t plus theta. Both are of different frequencies. Let me assume. Then P total means what is the total power absorbed by this R. See, these are some of the important relations, which is power total is equal to P1 plus P2 when omega 1 is not equal to omega 2 and theta can be anything. See, when both the frequencies are not same, if they are not equal and theta can be anything, means P total is equal to P1 plus P2. If P1 is the power due to only I1 of t and P2 is due to power only absorbed by resistor R, only when I2 of t is going to be present. But when if both are equal, if both the frequencies are equal and when theta is equal to 90, at this condition, then also power total is equal to P1 plus P2. But if omega 1 is equal to omega 2 and theta is less than 90, then definitely P total is not equal to P1 plus P2. So therefore we can say when omega 1 is not equal to omega 2, theta can be any value, then definitely power total is equal to P1 plus P2. But if both are equal, then definitely theta should be equal to 90, then only power total is equal to P1 plus P2. Otherwise, if they both are equal, if theta is less than 90, means definitely these are not equal. So therefore power total is equal to power absorbed by R due to I1 of t alone plus power absorbed by R due to I2 of t alone. In a network, due to one independent source, power dissipation in a particular resistor is P1 watt. Due to other independent source, power dissipation in a particular resistor is P2 watt. Then combined together, what is the total power dissipated in that element? So therefore, suppose there are a network with two sources. Because of one source acting alone, the power absorbed by that element is P1, and because of another source acting alone, the power absorbed by the same element is P2. Then what is the, if the both the sources are going to present, then what is the overall power absorbed by that element, which is under root over P1 plus or minus under root over P2 whole square. So this is the overall power this element can absorb, which is under root over P1 plus or minus under root over P2 whole square. When power factor angle is variable, shape of the current locus is semicircle. So here you are going to get a semicircle only when the power factor angle is variable. So whenever the power factor angle is variable, then definitely the shape of the current locus is semicircle. But when the power factor angle is a constant, shape of the current locus is a straight line. So the slope is constant means the power factor angle is a constant means angle theta is constant. So therefore always you are going to get a straight line. If it is a variable means you are going to get a semicircle. Otherwise you are going to get a straight line. If power factor is variable means theta is variable. So therefore you are going to get a semicircle. If power factor angle is a constant means theta is constant. So we can say that it is a straight line. Locus diagram can be either circle or straight line. So therefore here only two things you can get, either semicircle or circle, or you can get only a straight line, but not more than this. So therefore only these three diagrams you can get in a root locus. So therefore locus diagram, only these things you can, which are the semicircle or full circle or either straight line. Only these three things you can get, not more than this. Locus diagram of current in the circuit and the admittance of the circuit will be exactly same. See, the locus diagram of the current in the circuit and the admittance of the circuit will be exactly same. Just removing the voltage term in the current locus diagram, then we get the admittance locus diagram. So therefore I have already told you current is equal to voltage into admittance. So you can see clearly, if you remove V, the current locus diagram and the admittance locus diagram are both are same. Only thing is they are somewhat scaled. So current is scaled version of the admittance diagram. So therefore locus diagram of the current in the circuit and the admittance of the circuit will be exactly same. Just remove the voltage term in the current locus diagram, then we get the admittance locus diagram. Removing voltage term means keep V is equal to 1. Means removing means just keep the V is equal to 1. Then we are going to get the locus diagram of the admittance. And also admittance is equal to conductance plus J into susceptance. Superposition theorem means in any linear bilateral bidirectional circuit, bidirectional is also called as a bilateral circuit, having more than one independent source, the response in any one of the branches is equal to the algebraic sum of responses caused by individual sources, while the rest of the sources are replaced by its internal resistance. Don't do anything to the dependent sources. So therefore I have already told you, if any network contains of linear bilateral elements, then definitely the response at any branch because of so many sources acting simultaneously is equal to the algebraic sum of responses due to each and every source acting alone. So you don't have to do anything for a dependent source. Only independent sources are important in this theorem. So therefore, in any linear bidirectional circuit having more than one independent source, the response in any one of the branches is equal to the algebraic sum of the responses caused by individual sources, while the rest of the sources are replaced by its internal resistance. Means the remaining, suppose if you are going to think about voltage source replaced by internal voltage source means internal impedance means 0, whereas for current source ideal replaced by internal resistance means replaced by infinity. So therefore we can say clearly the ideal voltage source should be short circuit, whereas the ideal current source should be open circuit, because we have to replace them by their internal resistance, because the internal resistance of ideal voltage source is 0 and the internal resistance of ideal current source is infinity. So in any circuit, if you want to find what is the response of any branch in any branch because of so many sources acting simultaneously, then it is algebraic sum of the response due to each and every source acting alone. So the remaining sources should be replaced by their internal resistance. So always form factor is equal to, it's the ratio of the RMS value of the signal by the average value of the signal. So therefore form factor means, the easy way to remember is FRA, FRA. FRA means form factor is equal to ratio of the RMS value of the signal by the average value of the signal. Similarly, peak factor is also called as the crest factor, which is, it's a ratio of the maximum value of the voltage by the RMS value of the voltage. Means peak factor is also called as the crest factor. So therefore take a CMR. CMR means it is a crest factor, the peak factor is equal to the ratio of the maximum value of the signal by the RMS value of the signal. So you can see clearly here, FRA means Form factor is equal to ratio of the RMS value of the signal by the average value of the signal, whereas crest factor or the peak factor is equal to ratio of the maximum value of the signal to the RMS value of the signal. For sinusoidal signals, for pure sinusoidal signals, form factor is equal to ratio of the RMS value of the signal by the average value of the signal. So RMS value is Vm by root 2 and the average value is 2m by pi. So if you solve this one, we are going to get 1.11. Whereas peak factor is equal to, or crest factor is equal to CMR, maximum value by the average value, which is Vm by root 2. So if you solve this one, we are going to get root 2. So for pure sinusoidal signals, the form factor is equal to 1.11, the peak factor is equal to root 2. So it tells the shape of the waveforms and harmonics present or absent. See, basically this is going to tell you is the shape is purely sinusoidal or some harmonics are going to present. But suppose if the form factor is going to change from these ideal values, then we can say some amount of harmonics are going to injected in that waveform. In a series circuit, current is taken as a reference, whereas in the parallel circuit, voltage is taken as a difference, because in a series circuit, the current is same for each and every element. So because of that reason, we are going to take current as a reference, whereas in a parallel circuit, the voltage across each and every element is same. So because of that reason, we take voltage as the reference. For any passive element RLC, frequency of voltage and current waveform are always equal. So for any passive element RLC, the frequency of voltage and the current waveforms are always equal. So frequency of all voltage and current are always same for any passive network. And power waveform frequency is a double that of the voltage waveform frequency. So therefore, always the frequency of the power will be always a double that of the voltage or the current. So therefore, the frequency of voltage and current are always equal for any passive circuit, but the frequency of the power will be always double than that of the voltage or current. Suppose in India, frequency is equal to 50 Hz. This means that the voltage or current waveform, whatever the things we are going to get to our home, they are of frequency of 50 Hz. Whereas the frequency of the power will be twice of this one. So twice of this value, which is 2 into 50 is 100. So therefore we can say clearly the frequency of the voltage and the current is 50 Hz, whereas the frequency of the power is 100 Hz, because it is twice the frequency of current or voltage. Suppose the power dissipation in some element, if you are going to get, which is PD is equal to I square R, then make it function of R with the help of given circuit. So try to make this as a function of R with the help of the given circuit. Then if you want to know what is the PD by PR is equal to 0. So if you want to differentiate this value with respect to R, then rate of heat dissipation in that resistor is maximum. So therefore, at that value of R, you are going to get the maximum amount of dissipation in that resistor. So therefore, we can say clearly, try to make this equation in the terms of R and try to differentiate with respect to R. Then you are going to get, at that value of R, you are going to get the maximum amount of heat dissipation. The average value of the complete cycle of symmetrical wave is equal to 0. Yes, because the average value of the complete cycle of symmetrical wave is always equal to 0. So that is the reason only we have to consider only the half of the time period we need to consider, but not the full cycle. So while finding the average value of symmetrical waveform, for analysis only, half cycle is considered either voltage or current waveform. So therefore, that is the reason for a pure symmetrical waveform, we have to consider only the half of the waveform in order to figure out the average value, because otherwise it will become 0. While finding average value of the unsymmetrical waveform, complete cycle is considered. So therefore, for unsymmetrical waveform, we have to consider the full cycle, but not for the unsymmetrical. For the symmetrical waveform, we have to consider only the half cycle, but for unsymmetrical, we have to consider the full cycle. There is no term like PRMS, but only P average exists. The different names of the P average is. So always there is nothing like a PRMS term. Only average power is there, but not the RMS power. So the different names of the average power is real power, true power, effective power, and active power. So average power is also called as the real power, active power, true power, or effective power. These are the different names of the average power, like true power, active power, real power, effective power. So for a DC circuit, PDC is equal to I average square R for DC system, but for AC circuit, PAC is equal to IRMS square R. So replace I by I average for DC circuit, but replace I by IRMS for AC circuit. Suppose if f of t is a function of so many signals of different frequencies, so the condition is all these frequencies should be not same, they are all different. Then only the next signal f of the RMS value is equal to under root over summation of the squares of each and every RMS of the signal. So therefore, f RMS is equal to under root over f for RMS square plus f 2 RMS square plus up to like this. The only connection is all these signals should have different frequencies. If in data nothing mentioned, then by default meter reads RMS of the signal. So in the data, if they are not given what this signal is, what this meter is going to measure, then by default it is going to measure the RMS value of the signal. So when the dependent source value depends on the load, so when the dependent source value depends on the load component, then Thevenin's theorem cannot be applied. So you suppose here the dependent source, so there is some dependent source in the circuit and its value is going to depend upon the load, then you can't apply the Thevenin theorem for the circuit. And when the source is having unequal value of frequency, then Thevenin theorem cannot be applied to that circuit. See, even if a circuit is going to have different frequencies, then you can solve that question only by using the superposition but not by any other theorem. Similarly, when the mutual inductance depends on the load component, then also you can't apply the Thevenin theorem. So therefore, suppose there is a mutual inductance between two inductors, if it is going to depend upon the load, then also you can't apply the Thevenin's theorem. So these are some cases in which the Thevenin theorem can't be applied. In any network, after interchanging position of response and excitation, the ratio of response to excitation is constant, then given circuit satisfy the reciprocity theorem. So we can say that here, suppose if any given network, if you are going to interchange the response to excitation, if that ratio is still the same, then we are going to call it as the reciprocity theorem is satisfied, or we can say that network is reciprocal network. Some of the examples are response to excitation is current by voltage or voltage by current, but not current by current or voltage by voltage. So only here the ratio of the response to excitation must have some unit. If it is if it is having a unitless, then we can't apply that theorem. So therefore, here this theorem is only applicable for only if it is going to have some unit, which is ratio of the response to excitation. If it has some unit, then only we have to apply this theorem, which is current by voltage or voltage by current. So the current by voltage unit is mho, and the voltage by current ratio, the unit is ohm. So here for these two cases only, the reciprocity theorem is applicable, but not for this one, which is current by current is no unit and the voltage by voltage is no unit. So therefore, for this theorem is not applicable. So reciprocity theorem is not applicable for unitless. Only for unit we have to go for the application of the Thevenin theorem. If any dependent source is present in the circuit, then RTH will be negative. Suppose if any network, if it is going to have dependent sources, means then by using external source method we are going to get the RTH, then definitely in that RTH will be negative. Suppose if RTH is equal to positive, means absorbing power, example is induction motor. But if RTH is equal to negative, means it is delivering power, example is induction generator. So RTH is equal to positive means here that element is going to absorb the power, example is induction motor, because it is going to absorb the power. If RTH is equal to negative, means we can say clearly it is going to deliver the power, or simply some of the example is induction generator is going to deliver the active power, or it is going to accept the reactive power. RTH is equal to VTH by ISC. This method of calculation of RTH can be applied when the original network is having at least one independent source. I have already told you, if there is at least one independent source, then default you can apply RTH is equal to VTH by ISC, or external source method also you can applicable. Suppose there is some linear bilateral network. So the terminals of this linear bilateral network is A and B. So for these terminals we are going to apply some amount of external voltage of V, and the current is passing through is I. So I can replace this complex circuit by some Thevenin voltage and Thevenin resistance like this VTH and ITH. So now I can write the KVL in this equation, then I am going to get V is equal to VTH plus I into RTH. So with the help of means this circuit is now simplified into this circuit. So overall the behavior will be same. Duality does not mean that equivalence. Duality does not mean that equivalence, but it means mathematical representation of the both networks are identical. See, duality means only the circuits are not equal, but only the mathematical expressions of the circuits are equal. By using duality, it is possible to justify cost of the network. So by using that duality, we can know whether a mechanical, electrical is going to get applicable or not. So for every mechanical, electrical system is also going to get present. So what is the cost of that circuit can be easily approximated with the help of the duality. In the operation of circuit breakers, by satisfying the condition of transient free response, intensity of sparking can be reduced. So in the operation of circuit breakers, by satisfying the condition of transient free response, intensity of sparking can be reduced, because here in circuit breakers there will be a lot of amount of transient response. If you try to make a transient free response, then intensity of spark can be reduced. So therefore low cost devices can also be used. That is the reason a transient free response is best suited So therefore, sparking can be easily reduced. In RLC circuit, it is not possible to obtain transient free response because circuit is having two energy storage elements simultaneously, both charging and discharging conditions are present. So therefore, I see only for RL or RC only we can get a transient free response, but for RLC there are two energy storing elements, so we can't get a transient free condition for RLC series circuit because a charging and discharging are going to happen simultaneously. So because of that reason only, a transient free response is never possible in series RLC circuit. If you know value of degree, the way to convert into radians is you multiply by pi by 180. Then you are going to convert into radians. Some of the important Laplace transform formulas are for A signal. This is a time domain signals, and these are the Laplace transform, which is for A by S, e to the power of at means 1 by S minus A. Sin omega t means omega by S square plus omega square. For cos omega t, which is S by S square plus omega square, e to the power of at sin omega t means is e to the power of at into f of t. The Laplace transform is here f of S minus A. So wherever S is there, just replace S minus A. So for this we are going to get omega by S minus A whole square plus omega square. Then e to the power of minus 80 into cos omega t means replace whenever there is a function of e to the power of minus 80 into f of t, here replace S by S plus A, which is f of S plus A. So therefore we are going to get S plus A by S plus A whole square plus omega square. And similarly, the Laplace transform of d by dt of f of t is equal to S into f of S minus f of 0 minus. For u of t, the Laplace transform is 1 by S, and for delta of t, the Laplace transform is 1. And similarly, for u of t minus 5, which is here, suppose there is a function of f of t minus a into u of t minus a, then the Laplace transform will be e to the power of minus as into f of s. So by using this property, we can say e to the power of minus 5s into 1 by s. Similarly, for this one also, e to the power of minus 5s into 1. So now here I am going to discuss about the initial value theorem and the final value theorem. So initial value theorem is equal to f of 0 plus is equal to limit s tends to infinity s into f of s or limit t tends to 0 f of t. This is called as the initial value theorem. To apply initial value theorem, f of s numerator by denominator power should be greater than the numerator power. So always for the function f of s, the denominator function should be always greater than the numerator power. Then only you can apply the initial value theorem. So therefore, limit t tends to 0 f of t is equal to limit s tends to infinity s into f of s is equal to f of 0 plus. In order to apply the initial value theorem, always the Laplace transform of f of s, it is going to have the ratio of numerator to denominator. Always the denominator power should be always greater than the numerator power. Then only you can apply the initial value theorem. And whereas the final value theorem, which is f of infinity is equal to limit t tends to infinity f of t is equal to limit s tends to 0 s into f of s. Here, if any pole of f of s lies on imaginary axis or on the origins of S plane, then final value theorem will not be applicable. So therefore here the final value theorem will not applicable when the f of s is going to have any pole on the imaginary axis if any pole is going to have on the imaginary axis or on the origins of x-axis, then definitely we can say system is not a stable system. So because of that reason only we can say we can't apply this property. So therefore final initial value theorem is only applicable when the denominator power is greater than the numerator power, and also the final value theorem is going to applicable only when the poles of f of s are going to lie on the LHS of S plane purely. And similarly I am going to repeat again. See, the initial value theorem is going to applicable only when the Laplace transform of f of s is going to have a huge power in the denominator when compared to numerator. The final value theorem is going to applicable only when if the f of s is going to have all the poles strictly in the LHS of S plane, then only we can apply the final value theorem. Mesh analysis is applicable only to those networks which are planar and it uses Kirchhoff's voltage law. I have already told you mesh analysis is only applicable for the planar networks but not for the non-planar networks. Planar networks means even after redrawing there will be no crossovers, but for non-planar even after redrawing there will be crossovers. So but nodal analysis is applicable for both planar and also the non-planar networks. To define nature of power factor for any combination of the network, voltage phasor is taken as a reference since source voltage is always constant. So because voltage phasor we are going to take as a reference to figure out the power factor. If the current is going to lead the voltage means we are going to call it as a leading power factor. If the current is going to lag the current voltage means we are going to call it as a lagging power factor, because source voltage is almost constant. So because of that reason only we are going to take it as a reference. In practical systems, loads are connected in parallel So load voltage is always constant. So in the practical way, you can see all the loads are going to connect in parallel to the power system. So because of that reason only we can take voltage as constant. Power factor angle indicates the position of the current phasor with respect to the voltage phasor. So power factor angle means it is the angle between the current and also the voltage phasors. Power factor defines contribution of resistive load in the total load of the system. In the practical system, always high power factor is desirable. So the power factor means how much amount of resistive load is going to present in the overall system. If it is a very high means it's better. If the more the power factor, less the losses. So because of that reason only, it is always preferred to have higher power factor. So power factor defines contribution of resistive load in the total load of the system. In the practical system, always higher power factor is always desirable. If nothing is mentioned about the ammeter, then by default it reads RMS value. Suppose they are given some ammeter, and if they are not mentioned what it is going to measure, whether average value, whether RMS value, then definitely it is going to measure the RMS value. But for PMMC it is going to measure the average value, for MI and EMMC it is going to measure the RMS value. For RL series or parallel, the power factor is always lagging. Yes, for RL, whether it is a series or parallel, always the current is going to lag. So we simply say it is a lagging power factor. For AC, KVL and KCL used as phasor sum, whereas for DC, KVL and KCL used as arithmetic sum. So for DC analysis, we have to use KVL and KCL as arithmetic sum, whereas for AC circuits, we have to use KCL and KVL as vector sum or phasor sum. Suppose there is a load like this. For lagging load, suppose there is a lagging load, the power factor is cos theta 1 and the power consumed by the load is P1. Then we can write the complex power is equal to voltage into current whole power. So therefore we can say voltage into current whole conjugate. So therefore here we can write which is, so current is going to lag. So therefore I can write which is I bar is equal to mod of I into angle of minus theta 1 with respect to voltage. So we have to take the complex conjugate of this one. So we are going to get here mod V into mod I into angle of theta 1. So plus theta 1. So we can write V into I is nothing but the complex power magnitude value, which is P by cos phi. So therefore P1 by cos phi, cos theta 1 we are going to get the magnitude of the complex power, which is S bar is equal to P1 by cos theta 1 into angle of plus theta 1. Similarly for leading load, what will have? For leading load, suppose for leading load it will be same as this one, only replace your plus by minus. So for leading load cos theta 1 and P1, then S bar is equal to P by cos theta 1 angle of minus theta 1, because current is going to lead means positive, but we have to take the conjugate of that one, so it will be negative. So this will be again P1 by cos theta 1 is going to give you the magnitude of the complex power. Whenever there is a sudden change in applied voltage or load or changing stored energy in inductors and capacitors, transient will occur. See, transient is going to occur only when there is a sudden change in applied voltage or sudden change in load or sudden change in stored energy in the inductors or capacitors. At this condition only, a transient is going to occur. Inductance of air core solenoid is here L is equal to N square by R, where R is the reluctance of the core, which is L by mu A, which is here it is a air means mu R is equal to 1. So because of that reason only, which is L is equal to, if you simplify this one, we are going to get mu naught N square A by L. This is the inductance of the air core solenoid, where N is the number of turns on this air core coil, and also mu naught is equal to 4.10 to the power minus 7, where L is the length of the coil. Or you can say simply this is the length of the solenoid. Basically it is a solenoid but not the core. Basically the length of the solenoid but not the coil. This is basically the length of the solenoid but not the coil, which is L is the length of the solenoid but not the coil. So here R is equal to rho L by A. R is equal to rho L by A. So we can write A is equal to pi R square, or we can say pi into diameter of the diameter whole square. So therefore we can say 4 rho L by 4 pi d square. You can get this expression also. So therefore R is directly proportional to length by diameter whole square. So the T-port network we are going to get Z11 is equal to V1 by I1 when I2 is equal to 0. Similarly here in the, suppose if you want to know the transmission parameters, which is V1 is equal to A V2 minus B I2 and I1 is equal to C V2 minus D I2. Suppose when I2 is equal to 0, if you substitute here, we are going to get V1 is equal to AV2 and I1 is equal to CV2. So if you take the division of V1 by I1, we are going to get A by C. So therefore Z11 is equal to basically A by C. Energy stored in capacitor over a cycle when excited by an AC source is 0, because it stores energy in one half cycle and delivers that energy in the another half cycle. So therefore basically the overall energy stored in a capacitor in one cycle is completely 0, because for half of the time it is going to store the energy and remaining half of the time it is going to deliver the energy. So because of that reason only we can say the overall energy stored in the capacitor is 0. If network contains only resistance, the network is linear passive bilateral, so reciprocity theorem is satisfied. I've already told you, if a network is going to have only the resistance, means these are the linear elements and also passive elements, and the bilateral property is also satisfied. So we can say the reciprocity theorem is also going to get satisfied. So now here R2 is equal to R1 into 1 plus alpha into T2 minus T1. It is a basic relation which is where R1 is the resistance at T1 and R2 is the resistance at T2, where alpha is the coefficient factor, or we can say this is the thermal coefficient factor. Superposition principle is applicable on both time varying and the time invariant resistance. So superposition principle you can apply for both time varying and also for the time invariant elements. But it is not applicable for power calculation. It is only applicable for the voltage and the current calculations. So suppose if you take a parallelogram principle, this is F1 and this is F2, this is the overall vector is now F3. So therefore if you know this one, theta is the angle between the F2 and F1. So what is the overall length of this F3? So F3 square is equal to F1 square plus F2 square plus 2 F1 F2 cos theta. Theta is the angle between the F1 and F2. A network which obeys reciprocity theorem is called as the reciprocal network. See, any network which is going to satisfy the reciprocity theorem is called as a reciprocal network. And all passive networks are reciprocal networks. It's a very important point. I have already told you, any network is going to satisfy the reciprocity theorem is called as a reciprocal network. If the passive networks, means the network is going to contain only passive elements, because all passive elements are linear bilateral elements. So because of that reason it is going to even satisfy the reciprocal principle. So because of that we can say it is a reciprocity networks. So all passive networks are basically reciprocal networks because they are going to satisfy the reciprocity theorem. For a passive two-port network, output power can never be greater than the input power. So always for any passive elements, because some amount of energy is going to get lost, so we can conclude that always the output power will be always lesser than the input power. So these two formulas are very very important in the phasor analysis, which are sin phi. You can write sin phi as which is cos of 90 minus phi or cos of phi minus 90, whereas cos phi is equal to sin of phi plus 90. So this is a very important formula. If you want to convert sin to cos, use this formula, which is sin phi is equal to cos of 90 minus phi or cos of phi minus 90. Similarly, if you want cos phi, which is sin of 90 plus phi. So use these formulas if you want to convert sin to cos or cos to sin. So sin phi is equal to cos of phi minus 90, whereas cos phi is equal to sin of phi plus 90. Associative and bilaterality property are satisfied by a non-linear network. I have already told you, for a non-linear network, superposition principle is not satisfied, but associative and the bilaterality property are satisfied. I have already told you the operator of A is equal to 1 at an angle of plus 120. If you convert from this polar format to rectangular format, we are going to get minus of plus j root 3 by 2, and A square is equal to 1 at an angle of 240. If you convert this polar format to rectangular format, you are going to get minus of minus j root 3 by 2, and A cube is equal to 1, means 1 at an angle of 360 degree. So if you do the addition of all these things, we are going to get 1 plus A square plus A is equal to 0. Always capacitance is equal to area into permittivity by D. So therefore C is equal to epsilon A by D, where epsilon is equal to epsilon into epsilon R. So whereas epsilon R is called as the relative permittivity or dielectric constant. So therefore C is called as the capacitance, A is called as the area of the plate, and epsilon is called the permittivity of the medium, and D is called as the distance between the plates. Permittivity means the amount of opposition to a given electric field is called as the permittivity. A major advantage of active filters is that they can be realized without using the inductance. Means the basic advantage of active filters means they can be realized without using any inductor. Network made up of passive and linear time invariant elements are always reciprocal. I have already told you here, if any network is going to contain passive elements and they are time invariant, then definitely they are called as a reciprocal because they are going to satisfy the reciprocity theorem. The requirements for network to be reciprocal is, so what are the requirements for a network to be reciprocal? A network should only have only single source it should present, and also network should have only not have any dependent sources, and also network must be made up of only passive and linear time invariant elements. So therefore a reciprocal theorem is satisfied only if it is going to have only one independent source and there will be no dependent sources, and there must be only passive and linear time invariant elements. Then only a reciprocal theorem is satisfied, and we can say that network is said to be reciprocal network. Networks that contain many series connected elements, voltage source or meshes having common current source super meshes are more suitable for mesh analysis than for nodal analysis. Means if any circuit which is going to have more number of meshes, it is preferred for mesh analysis rather than the nodal analysis. So network that containing many series connected elements, voltage sources or meshes having common current sources or super meshes are more suitable for mesh analysis than for the nodal analysis. Networks with parallel connected systems, current sources or nodes connected by voltage sources are more suitable for the nodal analysis rather than the mesh analysis. Means if any circuit which is going to contain more number of meshes, then we can say it is best to use the mesh analysis. But if any network is going to contain more number of voltages across the nodes, then it is preferred to use the nodal analysis rather than the mesh analysis. A circuit with fewer nodes than meshes is better analyzed by nodal analysis than the mesh analysis. A circuit with fewer nodes than meshes is better analyzed using nodal analysis rather than the mesh analysis, because if a circuit is going to have less nodes compared to meshes, means the less number of equations with respect to nodal analysis rather than the number of equations with respect to mesh analysis. So within a small time you can solve that question with the help of the nodal analysis. Similarly, a circuit with fewer meshes than nodes is better analyzed using the mesh analysis rather than the nodal analysis. Means if any circuit is going to have less number of meshes, means less number of equations with respect to mesh analysis. If there are more nodes, means more equations with respect to nodal analysis, so therefore it is preferred for mesh analysis rather than the nodal analysis if the number of meshes are lesser than the nodes. In any linear planar network, number of independent KVL equations are equal to number of links. I have already told you here the number of independent KVL equations is equal to the number of links, which is L is equal to B minus of N minus 1, and the number of independent KCL equations is equal to number of peaks. So number of KVL equations is equal to number of links, as the number of KCL equations is equal to number of peaks, which is equal to N minus 1. In nodal analysis, the preferred reference node is a node that is connected to many parts of the network. So in the nodal analysis, the preferred reference node is a node that is connected to many parts of the network. If that node is connected to many parts of the network, that is preferred to choose as the reference node. Two networks are said to be dual when the loop equations of one network are analogous to the node equations of the another. It's a very important point here. Here, two networks are said to be dual means here if the loop equations of one network is equal to the node equations of the another network, then only we can say that these two networks are said to be dual. So, two networks are said to be dual only when the loop equations of one network are analogous to the node equations of the other network. Mesh analysis is valid only for planar networks. I have already told you mesh analysis is only applicable for planar networks but not for the non-planar networks. Whereas the nodal analysis is applicable for both the mesh for the planar networks and also for the non-planar networks. Non-linear networks satisfy associative and the bilateral property. As I have already told you, a non-linear network will satisfy both the associative but the bilateral but not the superposition principle. If Thevenin equivalent of a circuit is known, then its Norton equivalent is also known because Norton's equivalent is the dual of the Thevenin's equivalent. See, if you know Thevenin equivalent, then you can easily find the Norton equivalent because they are both dual to each other. Superposition theorem is valid only for linear networks and the Diligence theorem is valid irrespective of the type of network and irrespective of. So, superposition theorem is valid only for linear networks. It is valid only for the linear networks, and Diligence theorem is valid irrespective of the type of network and irrespective of the type of element. No matter whatever the type of the network and the type of the element, always Diligence theorem is going to be valid. But superposition theorem is going to be valid only for the linear networks, irrespective of the type of element, whether passive element or independent sources or dependent sources. So always irrespective of the elements, the Diligence theorem is going to be applicable. For superposition theorem is going to be valid only if the network is going to consist only on the linear elements. Any four-terminal passive network can be converted to equivalent T or pi network. So therefore we can say clearly any four-terminal passive network can be connected to equivalent T or pi. So you can do the conversion from star to delta or delta to star. Thevenin's theorem or Norton's theorem can be used to get a transfer function. Yes, Thevenin's theorem or the Norton theorem can be used to get a transfer function. Reciprocity theorem is applicable for linear and bilateral networks. I have already told you reciprocity theorem is satisfied only when the circuit is going to have only one independent source, there are no dependent sources, and all the elements of the network are purely passive and linear and bilateral. Then only we can say the reciprocity theorem is satisfied, and we can say it is a reciprocal network. Diligence theorem is applicable to any network made up of lumped terminal element. The circuit's elements can be linear or non-linear, time variant or time invariant, dependent sources or independent sources. No matter what are the elements, any network is going to satisfy the diligence theorem. The current in a constant inductive system does not change instantaneously because flux linkage is conserved. Because here in an inductor, current can't change instantaneously because here the main reason is flux is always conserved, means it can't change instantaneously. So because of that is only current in an inductor can't change instantaneously. The power factor of a circuit in which voltage and current waves are non-sinusoidal. So suppose if a circuit is going to contain voltage and current are non-sinusoidal, then it is defined as the cosine of the angle of the phase difference between the equivalent waves having respect to sine wave RMS values of equal to those of the voltage and current in the circuit. So listen this point carefully. The power factor of a circuit in which the voltage and the current waves are non-sinusoidal is defined as the cos of the angle of the phase difference between the two equivalent sine waves having respectively RMS values equal to those of the voltage and the current in the circuit. So here how to find the RMS of two voltage and current waveform if they are non-sinusoidal means it is the cos of the angle between the effective value of the RMS value of these two signals that you need to take. Transients are caused because the load is suddenly connected or disconnected from the supply. So whenever there is a sudden change in the load, then only we are going to get the transient, or sudden change in the energy stored in the elements, then also we are going to get the transients, or sudden change in the variation of the supply also, then also we are going to get the transients. The change in stored energy in the inductors and the capacitors. So now we are going to learn about the Q is called the quality factor and zeta is called as the damping ratio. The relation between these two is called Q is equal to 1 by 2 zeta, or zeta is equal to 1 by 2 Q. See, when zeta is equal to 1, Q is equal to half. When zeta is less than 1 means we can say this is Q is greater than half. When zeta is greater than 1 means Q is less than half. We can get from here. So zeta is equal to 1 means it is a critically damped system. When zeta is less than 1, it is a under damped system. When zeta is greater than 1 means it is a over damped system. In a series RLC circuit, the current is maximum at resonant frequency. Yes, in a series RLC circuit, the current is maximum at resonant frequency, whereas it is minimum for a parallel RLC circuit. And the maximum voltage across the capacitor occurs at a frequency lower than the resonance frequency. I have already told you in a series RLC circuit, the maximum voltage is going to occur in a capacitor when it is lesser than the resonant frequency, whereas for inductor it is going to occur above the resonant frequency. So the maximum voltage across the capacitor occurs at a frequency lower than the resonant frequency, and the maximum voltage across the inductor occurs at a frequency higher than the resonant frequency. These points I have already discussed in a series RLC circuit. A short in any of the circuit causes the total circuit resistance to decrease, and thereby the current will increase. So if you do the short across any 2 points, the overall resistance is going to get decrease, means we are going to the current is going to get increase, because they are inversely proportional. So therefore any short in any of the circuit is going to decrease the resistance, overall resistance. So therefore current is going to get increase. So these are some of the important points of network analysis which are frequently asked in any of the competitive examinations. So if you like the content of our channel, then please do like, share and subscribe to our YouTube channel, and don't forget to press the bell icon button. So whenever we upload a new video, the direct notification comes from mobile. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smiling and take care. Bye bye.